to. Eh.
Just leave it on for now. Is that the best?
That's fine.
Okay.
Yeah, we're going to control it.
Oh, okay.
Yeah.
Speakers is already on. Hi, Roger. Okay.
An interesting thing to do.
So, Richard, there's a timer there which they can see. Okay. We can't really see. I was going to time on my phone.
Yeah. No, indeed. But they can see. I think you can see if you look at the Slack channel. People online.
I would really, really like to keep it all on Zoom if at all possible.
So you're joining by Zoom.
I'm connected by Zoom as are two of our key speakers, which is excellent.
Yeah. Well, I'm sure the guys. So I am checking. So it's
Yeah. Yes. So, who's Nora? Oh, right. But I'll rather than have time to watch two channels at once. And since we not all the participants and are pretty apparent. That was exactly what I wanted to do. Yes. Yeah. Exactly the plan. Leave a couple of questions. We're slightly more relaxed on time because people will not have the presentation's loaded, but they
I see, but they're not heard.
but they can't do it. So.
Well, it's funny because it's the middle of the day.
They didn't register, and they couldn't register. Why did you come back there? Hey, how are you? Good to see you. Cool that you could come all the way here.
Very glad I got on school on Saturday to attend stuff this week.
Oh, okay.
How you doing?
Well, we started 10 days before the first week because my wife and I went on safari.
That's great.
Last week, 2 at a time, so it's all busy now.
I'm gonna do that at the end of the not that quite that intensive, like a couple of days like last week. So
It's worth it. As long as we're here, right? Other continents.
yeah.
Okay. All our speakers are online, checked in, communicating.
Okay. So how are we doing? 2 minutes?
One.
1 minute. 1 minute.
We'll do ourselves a favor and start at one time, right?
Yeah, exactly.
Not a lot of people online, but I will. Not surprising.
Okay, good morning, everybody. If you'd like to take your seats, we can start. We may as well make a start on time. So welcome, everybody, and welcome to everybody online. This is the first of 4 sessions organized by the Working Group on Global Coordination of Ground and Space-Based Astrophysics, of which I am the co-chair. I'm Roger Davies from the University of Oxford, and my co-chair is Rachel Somerville from the Flatiron Institute. Rachel isn't here this week, but she certainly contributed to making the program. So just so that you know what's coming, just in case, we have this session on future space missions, and then at 1:30 we have a session on future ground-based facilities. And the final session for today at 3:30 is on far infrared and millimeter facilities. And then tomorrow morning, in the equivalent of this session, we have a session which is kind of a follow-up of a previous Kavli workshop on coordination of transient follow-up with LIGO and Rubin. And so that's the program for the 4 sessions. Inevitably, we're not able to cover all varieties of project that could come under the headings that I've given, but we do our best to cover the big important things with upcoming issues and questions to address. So this is your opportunity to ask the leaders of many of these projects questions throughout. So I hope you take that opportunity both online and in the room. And having said all that, and starting on time, I think the best thing I can do now is to hand over to Richard Green. I'm very grateful to Richard for chairing this session and putting the program together. Richard.
Thanks, Roger. Just to give everyone a sort of sense of the plan, we have 4 speakers this morning, and we will leave just a little bit of time at the end of their talks for some factual-like questions, and then we have a generous amount of time at the end of the session for your questions and some questions we have for them as a panel. So speakers, if you have 15 minutes, I'll give you a 5-minute warning, and if it's a 10 minutes, I'll give a 3-minute warning, and so we can, and for those online, not in the room, please use the Zoom chat to ask your questions, and I will be monitoring that. I understand that people with less gray hair also like the Slack channel, but watching one thing is fine for me. So let's please just concentrate on Zoom. Okay, and so with that, let's kick this off. We are very fortunate to have today Mark Clampin, who's the Division Director for Astrophysics in NASA Science Mission Directorate. So, Mark.
Okay, good morning, everybody. It's a great pleasure to be here. So I'm going to follow the direction I was given, which is to give an overview of where we are in NASA astrophysics, where we're going in the future. I just wanted to start off by reminding people these are the big questions that NASA astrophysics tries to address. How does the universe work? How did we get here? Are we alone? We've been working to these questions for a very long time now. And in practice, what that means is that every decade we get a decadal survey that gives us the direction on the key questions we should be addressing in a given decade. And I think most people would agree, certainly for NASA astrophysics, this has always worked very well. It's given us pretty much a flagship every decade and allowed us to focus on other key science goals that the decadal survey recommends. And my job is certainly to follow that approach. So just as a quick reminder, in 1972, the decadal survey gave us the Hubble Space Telescope. I'm going to jump around here. 2000, it gave us the James Webb Space Telescope. And right now, the current program, a record, is the Roman Space Telescope, which was recommended in 2010. And I'll come back to the 2020 decadal survey towards the end. But it basically identified 3 major objectives for this decade. One is a large space telescope that would search for life in the universe, an emphasis on time domain and multi-messenger astrophysics. And for the session tomorrow, I'd strongly encourage discussion of how Rubin and the ground-based facilities also tie into NASA assets, because one thing that keeps me awake at night is when Rubin produces this absolute flood of transients, how does NASA deal with that when we cannot just be slewing our assets around the sky non-stop to do follow-up? So we're working very closely with our ground-based colleagues to put in place an infrastructure so that we can do alerts and can sort of filter down those alerts to the ones that really need to be targeted as, for instance, director's discretionary time on the larger missions. So there's a lot of work going in there, and we can come back to that tomorrow. And then the other recommendation is the astrophysics probes. So I'm not going to speak too much more about those, primarily because the competition is actually underway, but the recommendation was a new line in the NASA astrophysics budget for astrophysics probes. The PI cost cap, or the cost of these missions, would be about $1 billion. And we were told by the decadal to solicit proposals for far infrared or X-ray missions, and that's imaging or spectroscopy for both wavelengths. That is what we have done. We are in the process right now of making a selection. We expect to announce our initial down select, we hope, of 2 missions by the end of the year, and they will then do a step 1 study, as we call them, or phase A, and in about a year we'll make the final down select, and it will be done based on the science and on the technical feasibility of the mission. So I just wanted to remind you, we do a lot of different things in astrophysics. So in addition to operating 15 missions and currently developing around 18 missions in different scales, we also develop technology. The only way we advance astrophysics for NASA missions is by developing technology, and we have to do much of that investment ourselves because nobody else is going to do it for us. And it's really the technology that allows us to make that next science jump with these missions. We also support a very active research and analysis program, so that's research that gets done using the data that comes down from our operating missions. You'll see those in a minute. And it's also technology, and then everything you see on the right-hand side, smaller missions such as CubeSats that are done under our APRA program, sounding rocket missions, and also balloons. And we're emphasizing balloons quite a bit here because, we have some crossover there with our South African colleagues. And all of the things on the right-hand side we see as really great ways of training the next generation of astrophysicists and also the next generation of scientists who are going to build instruments and help contribute to future flagships or explorer class missions. So we also really focus on making sure that we are putting in place the infrastructure and the facilities so that we can train the next generation of scientists and also engineers as well. This is how our current mission classes break down. So generally the decadal survey missions or great observatories, flagships, whatever you want to call them, typically are something like $2.5 billion or over. We've just added, as I said, this new medium class. This is the probe. The PI cost cap is $1 billion. The actual cost of the mission, of course, is a bit larger than that because we actually have to get it into space. So the 1.5 includes the cost of the launcher. For the explorers, we have our medium class explorers, and a good example of that is the TESS mission, or the small explorers here. A good example is New Star or IXPE, which are both X-ray missions. And then until recently, we had our small class missions of opportunity, which are about 80 million, and they can generally be an instrument or just a very small investigation. We have not done a selection on the most recent mission of opportunity, and we will not be doing one in 2025, and that's because of budget issues with the current NASA budget, where we're working since 25 on a flat budget, which basically means that we're having to find reductions in a number of our missions just to get, to keep moving forward, make sure that we are addressing the decadal recommendations as well as maintaining a lot of these capabilities. The research missions are the ones that we do under RNA, and I just want to point to the Pioneers. So Pioneers was a new program that was started about 3 or 4 years ago. These are $20 million class missions. They're generally used as ride shares. So the idea is that most of these missions will go on a ride share with something else. So we also hopefully cut the cost of launch quite a bit. And they are designed for first-time PIs, early career scientists and engineers. and they make a great way of training the next generation. They also, of course, do really good scientific investigations, and probably the first one that we will fly will be PUEO, which is a balloon-borne mission. So these can be CubeSats, small satellites, or balloons. And then down at the bottom, as I already said, you know, we have our suborbital rockets, balloons, and CubeSats. On the right, you see our international collaborations, and these pretty much are put in place, you know, as we talk to our international partners, as we have the resources, and we see those as a great way of working with our partners to broaden our reach across other astrophysics investigations by making some kind of resource investment that allows us to benefit and our partners to benefit. And some good examples there, Euclid, where we provided one of the focal plane arrays. We're also providing the focal plane array for XRISM, and that's actually one of the very first quantum sensors ever flown in space, so we're really excited about that. And of course, going forward, we'll be partnering with ESA on the LISA mission, which is a gravitational wave opportunity. So this is what the astrophysics fleet looks like. All of the missions in purple are what we call extended life missions. They pass their nominal operating lifetime, continue to do science, and we continue to maintain RNA programs that support them. Webb, Euclid, and XRISM are all in their prime mission operation phase right now. And then you can see down below, we have a number of missions that are in the pipeline, either in formulation or development, which actually means people are bolting them together, to put it very crudely. SphereX is a really good example. That's our next mid-class Explorer launch. And you also see Roman there, which I'll come back to in a minute. So let me move on. So I said the next program of record is Roman. Roman is a very different kind of mission for us. It's a flagship, but it's our very first survey flagship. So we're having to kind of step back and think very carefully about how do we do the science with Roman, and how do we make sure that our whole community has equitable access to the data and has equitable opportunities to be able to reduce the data. So we're putting a lot of time and effort right now into making sure that we have a cloud and cloud computing for the whole science community to use. And we're also changing very much the paradigm about how we do the awards for these particular missions. I did just want to highlight very quickly, the Roman Space Telescope also has a tech demonstration instrument called the CGI, or the Coronagraphic Imager. That has just been delivered. Its goal is to demonstrate active control of the wavefront to achieve a contrast of around 10 to the 7 in orbit. You can see the instrument in the middle. It's an extremely complex instrument. It was developed and built at JPL. On the right, you can see the filter wheel with all the coronagraphic masks and pupils. And on the left, you can see an example of what we call digging a dark hole, or increasing the contrast around the mask. And they're already demonstrating in the thermal vacuum testing an order of magnitude better than the requirement. So that's going really well. Just for grins, this is our next mid-X mission. You know, it's got a very strange appearance compared to most space missions. And this is because it's a low Earth orbit mission that's using passive cooling to do its infrared imaging. So this is a JPL Caltech mission. It will basically do an all-sky spectroscopic survey. And we really expect our mid-X's to produce a lot of data that is a broader benefit to the community than just the science investigation being done by the principal investigator science team. So this is, we think, a really good example of what a mid-X should be. I'm going to spin on. Oops, So just to finish up, I'll say a few words about habitable worlds. So this is the flagship mission concept recommended by the Astro 2020 Decadal Survey. You see here very notional architecture. We have not started designing this yet. We're following the recommendation in the Decadal Survey, which is mature the technologies and then start designing the telescope. So we think one of the lessons learned from Webb is not to try to design while you're maturing technologies, because these large flagships are very complex systems. And if you don't build them in the right order by understanding the technologies before you start designing, you kind of find you have a lot of requirement mismatches, which then require further development later on. So we are starting off with a Habitable Worlds Observatory Technology Maturation Program. We got told in the most recent congressional budget to create a project office, which started on the 1st of August at the Goddard Space Flight Center. So we are really moving forward with this program. And the Goddard Space Flight Center is currently working on putting together all of the technology roadmaps, working with our colleagues at JPL, who will do the coronagraph, and identifying the milestones and then the requirements for the National Academy's review that says we can go into the design phase, which we're expecting will be towards the end of the decade. So I will stop there and take questions.
Good questions for Mark? Not at all.
So in keeping with the spirit of the session, with Ruben, of course, being the line the challenge of launch. So how do you vision coordinate the data collection, analysis?
So if you're specifically talking about time domain and multi-messenger, we've done a number of things. So we've made a number of investments at NASA centers that have traditionally been the centers that focus on high energy astrophysics and time domain activities. So both Goddard and Marshall are putting together what we call a sort of GCN network, or I wouldn't say putting it together, they're upgrading it so it's not sort of relying on FTP and lots of IT that nobody likes to use anymore. So we've upgraded the alert network on the NASA side, and we're currently working with Rubin to make sure that that network can plug into the different brokers who will be doing Rubin data. We're also, every 6 months or so, conducting an international working group which comprises the NSF, NASA, ESA, and then a lot of space agencies, including most of the European ones, as well as ESA, the Indian Space Agency, Israeli Space Agency, and we're trying to coordinate how we do time domain astronomy across all of these nations so that we're not all building the same mission or all trying to do the same particular piece of the TDAM puzzle and leaving the rest of it sort of untouched. So we're trying to coordinate and make sure we have a more globally focused approach to doing this.
Thanks, Mark. The international community has a large heliophysics effort going on as well, and I was just curious how much of that effort has crosstalk with what you manage.
So I would say that we have a number of missions that are looking at what you would call stellar activity as it relates to doing exoplanet science. NASA, of course, has its own heliophysics division, and all of the sort of global space weather and related science is done under the auspices of the heliophysics division, and we work very closely with them. And there's clearly more and more crossover. One of the things that we recently did was hire David Grinspoon, who's an astrobiologist, and he is actually trying to coordinate between my division, heliophysics, and planetary, a better sort of big picture look at exoplanets, not just from the perspective of the kind of missions we build like TESS, but also looking at stellar activity, and then on the planetary side bringing in what we've learned about our own solar system, so we have a more holistic picture of what an exoplanet environment might be, especially given most of the JWST targets right now are low mass M stars, which are extremely active.
We'll have more time during the discussion period, so let's thank Mark again. Our next speaker will be Nora Litzkendorf. She's the coordinator of the European Space Agency Astronomy Working Group. So...
Can you hear me?
Yes, we can. And if you can show Nora's slides, and Nora, you'll need to say next slide as these guys get things going.
Okay, I mean, before I see my slides, I can introduce myself real quick. My name is Nora Lützgendorf. I am project scientist at the European Space Agency for our mission LISA, but I also work in science coordination, as just mentioned, as the executive secretary of the Astronomy Working Group. So this is one of our advisory bodies. And with this group, we are advising basically ESA what we do in science for extensions and also for adoptions of missions. So that is my role. And in this capacity, I would like to present if I see my slides soon. That looks promising. Perfect. Okay, thank you. So then we can actually move directly to the next slide. I will talk about the ESA Science Program and our future missions. And if I can get the next slide. Yeah, perfect. Just a quick reminder who we are. We are the European Space Agency. We were founded almost 50 years ago by 10 member states in Europe who wanted to combine forces to really do all the amazing, ambitious space programs that we are doing today. Nowadays, we're 22 member states, over 5,000 employees, and we are there for exploration and use of space for exclusively peaceful purposes. We have 7 sites across Europe and the spaceport in French Guiana. Our budget is a little bit below 8 billion per year, which comes down to 14 euro per European per year. So this is as much as a movie theater ticket nowadays. Next slide, please. So before I talk about our future missions, I wanted to give you a little bit of our terminology. Similar to NASA, we also have different types of missions. We start with the large missions. Those are our flagship missions, our billion-euro class missions. They have usually a cadence of 6 to 7 years. There are exceptions, and I will talk about them in a second. Then we have the medium missions. Those are also ESA-led or contributions to international collaborations, and they have a cadence of 3 to 4 years. They also shorten their development time, so that gives them a little bit more flexibility. And then speaking of flexibility, our most flexible missions are the small and fast missions. Again, they can be ESA-led or they can be contributions to member states. They can also be launched as passengers with other missions, so really little hitchhikers on the rockets that launch bigger missions to save money. We also have missions of opportunity where we provide non-mission critical contribution to partner-led missions. Currently, we had launched 41 missions, and this includes also our partner missions. So not all of those missions were launched from our facilities. 19 missions are currently in operations. Like one of our latest ones, Euclid, just launched last year, and 22 are in a legacy phase, such as COTS-B, which was one of our first missions in 1975. That means they're decommissioned and not being used anymore. And then we have 14 missions currently in the pipeline, so they are in the study and the development phase. So next slide, please. So this is our, I see it always twice. This is our cosmic observers. This is the fleet that we use for observing astrophysical events. We also have the solar system explorers that I will talk about in a second. And how this slide works is you have on the uppermost row, you have the missions in development. So such as Ariel, Arrakis, Plato, and so on. Our big missions, New Athena and Lisa, I will talk about in a second. Then we have the active missions, so it's Gaia, Cheops, and Euclid. And then we have our legacy mission on the bottom. We also, we have a very nice coverage of the electromagnetic spectrum and beyond. We also have Lisa in the pipeline, and I will talk about this. And we had Lisa Pathfinder to really test the concept of gravitational wave physics, and Microscope, which was a collaboration where we looked at free fall. So really fundamental physics. Next slide, please. And here are our solar system explorers. Again, we have up in development, active, and legacy missions. And this time we show where they actually go in our solar system. So these are the explorers that go to our neighboring planets and beyond. You can see we haven't explored much further beyond Saturn. So this is definitely still something to look at in the future. Our latest big mission just launched last year, JUICE, is going to Jupiter, and we'll look at its icy moons. So that's going to be very exciting. I also want to highlight one of our legacy missions, Rosetta, that you probably all remember. That was the one that landed on a comet, and that was a very successful mission. You can see we have many heliophysics missions that are all looking at the sun in one way or the other. We also have Cluster, which is looking at our plasma of the Earth with 4 different spacecraft. So I want to talk about some of those missions in more detail. I don't have time to talk all of our future missions. I would love to, but I don't have time. So I picked the ones that I personally find the most exciting, but also the ones that are our flagship missions right now. And that's definitely something to keep an eye out for. So if we go to the next slide, please. So first of all, I want to talk about LISA. And again, I'm very biased. I'm project scientist for this mission. This is our gravitational wave observatory in space. The first time we will do something like this in space. LISA has 3 spacecraft that fly in a triangular formation, either leading or trailing Earth, while they're being on their own individual orbit. So that triangle is basically just a coincidence. But we need that triangle to measure the distance between our free-floating golden cubes that we have in the spacecraft to measure like minuscule little changes in the distances between objects, because that is what gravitational waves do. And to just give you an idea of the numbers, the distance between our spacecraft and our test cubes is 2.5 million kilometers. We will be measuring this distance changes in the order of picometer, so 10 to the minus 12. So it's as big as a helium atom, basically. So this is a technological marvel. We have tested some of this with LISA Pathfinder already, and we are pretty confident that we can do this. But it's not just amazing because of technology and because of we are doing this for the first time. It is also from the astrophysics side. We are going to observe a complete new window of gravitational waves that we cannot access from the ground. We will be looking at supermassive black hole mergers. We will see tens of thousands of galactic binaries around us. And we see exotic objects such as extreme mass ratio in spirals and things like that, and hopefully new things that we didn't expect. So LISA is one of those things. I mean, how often can you say that we've never done this before in space? And this is really exciting for this mission for us to come. It had a long way till now. We just passed a very major milestone where we have now passed adoption and go into now implementation, where we pick a prime contractor and then we'll actually build the mission. So this is going to be very exciting. Launch is planned for 2035, so it's still a way to go, but I think we are on a very good track. Next slide, please. So speaking of large missions, LISA is one of our large missions. JUICE is the other one, and the other third one we have is New Athena. New Athena is going to be our next big X-ray telescope in space. It's going to be the biggest one ever flown. You can see size comparisons here with Eximum Newton. And it will have some really exciting instruments on board that allow us to completely change the field of X-ray astronomy for many, many objects. So we have an X-ray integral field unit to get spectra of our objects, and we have a wide field imager. New Athena will go to L2. And here is the timeline is also pretty close to LISA. So we will be looking at the launch in 2037. So only 2 years after LISA. And as said, there are exceptions for our cadence for L missions. This is one, because LISA and Athena actually will work absolutely amazing together. They can do multi-messenger astronomy. We will be able to alert Athena when we see a supermassive black hole merging with LISA, and we can look at the afterglow emissions that we expect in the X-ray. But there's many more things that New Athena can do. Obviously, it will also look at hot gas in the cosmic web and high energy astrophysical events, such as kilonovae. And again, a good opportunity to do multi-messenger here in this time with ground-based gravitational wave observatories. So very exciting. We are just a few years behind with Athena compared to LISA, but they're both on their best track right now to get launched at the dedicated dates. Next slide, please. And the last mission from this program I wanted to talk about is Envision. That's our next mission to Venus. This is an M mission. So it will be a little bit faster. It will be launching in the early 30s. So 31 is right now the plan, I think. And Envision will go and will scan Venus to its core, like literally. It will not just look at the atmosphere. It has many amazing instruments on board to also look at the subsurface, to measure its gravitational field, to look for volcanic activity. We have 3 spectrographs on board that can look for volcanic blooms. And it's really the point of this mission is to look at the history of this planet, see if there was maybe some possibility of life at some point. Maybe it was cool enough to have water. And all those questions will be answered with Envision. So this is a very exciting mission for our solar system exploration. And again, the launch is planned for 31, and then we have about an 18-month cruise phase until we arrive there. Okay, next slide, please. So those were the missions I wanted to talk about from our Cosmic Vision program. Again, there's many more, and I could talk about this forever, but I don't have enough time. I just wanted to show you our Cosmic Vision program because it's starting to run out. Our last launch is in 2037 with New Athena. Many of our missions, small, medium, and large, are already on their way to be launched. Only 2 of them are still in study phase. So we need to start thinking now what we're going to do in the next 10 years from the 2030s. And what is our next big plan? Same as with the decadals, we always have, we ask our community what is happening next, what are the big questions we want to answer, and what missions we want to build. So we go to the next slide, please. And that is what we call Voyage 2050. This was an expert committee report, basically advising ESA on what are the next big science goals we want to do. And the 3 of them you can see here. Those are the moons of the giant planets. Obviously, they're super exciting. They have those water reservoirs. They might have life and biotraces, but it's hard to get to them. But this is a very ambitious goal. Then we have from temperate exoplanets to the Milky Way. And that is basically looking at Earth-like exoplanets in the infrared, or doing another survey, Gaia-like survey in the infrared, to really map our galaxy beyond the places where Gaia could look. And then we have new physical probes of the early universe. And that obviously includes gravitational waves. This is a new physical probe that we haven't used that much for, especially the very high Z universe. But also cosmic microwave background is something we want to maybe look at it again and do a spectroscopy of it and do more also gravitational wave observations beyond LISA in different windows in frequency. So those are all our ideas. We have just recently made a very important step towards this goal with selecting, or at least thinking about our next big, large flagship mission. And if I can see the next slide, please. And that is going...
Nora,
yeah?
5-minute warning.
Okay, that's fine. Thank you. So yeah, we are actually now looking at the moons of the giant planets, and I can see the next slide from this, please. And our next big mission will go to Enceladus. This is really hot off the press. That was just decided this year that it should be Enceladus. It should be the goal of our next L mission, our next flagship mission. And Enceladus is super exciting because it has those plumes that you can see from space. So it has water. It has a water reservoir that connects to the surface and probably to the core. There's not much we know about it yet. And that's why we want to go there, and we actually want to land on it. And that is a very ambitious plan, because to have a lander and an orbiter and the propulsion it brings you to Saturn is really, it's a very heavy object. So we cannot launch this on a single rocket. Our plan is to launch 2 rockets, 2 Ariane 6 rockets, have a rendezvous in space, connect those 2 things, and then travel to Saturn. Then get rid of our propulsion module again, have flybys of all of the Saturn moons, or the big moons, sample the plumes in space, and then land on the surface of Enceladus. So you can read the whole report. I put the link in the bottom. There's a PDF that really describes why we want to go to Enceladus and how we are planning to do this. And yeah, that is super exciting. This is obviously still a way away from here. The plan right now is to launch in the early 40s and to arrive in the mid 50s. But it is very important that we think about this now, how we can do the technology and how we make this happen to really explore those parts of our solar system that we don't know that much about. So yeah, very exciting. Next slide, please. And speaking of Voyage 2050, I have also some M missions that are currently in the pipeline. With our M missions, we down select always from a big pool of missions to smaller numbers. Currently have 3 missions that we have in the phase A study. So they will be studied, and then in the mid-26, we will select one of them to go further into implementation. And those 3 are M-MATIS, which is going to study the Mars atmosphere, so the ionosphere, the thermosphere, and the magnetosphere with 2 different spacecrafts going around Mars. Then we have the Plasma Observatory, which is basically a successor to our cluster mission, now using 7 spacecrafts instead of 4 to really go down in the absolute minuscule scales of plasma interactions with the larger scales. And then we have the CEOS, which is a high energy mission that looks at gamma ray bursts near and far. And that again would open a really nice window for multi-messenger astronomy. So we don't know which one it's going to be. Right now, they're all 3 studied, but keep an eye open. We probably also have a new call for either M or F missions very soon so that the community can propose new missions. And with that, I get to my last slide. Just for you to know how you can connect with the ESA Science. We have many, many ways of the community to follow us and to interact with us. If you want to know more about our missions and when those mission calls come out, I would highly recommend to subscribe to our newsletter. We also have a very amazing space science research fellowship for our more junior members of the community. If you want to do your postdoc and you are a national of our member states, you can apply to this program. It is absolutely fantastic to be close to the ESA missions and see how those missions work. We also have traineeships, and we have a page dedicated for announcements of opportunity. So again, mission calls for science teams, for the astronomy working group. If you want to be part of the advisory system, all of this can be found there. And with this, I hope to see you there and leave it open for questions. Thank you.
Questions for Nora about that ambitious program?
Thank you. Yes, it's certainly an ambitious program. My question really is, sorry, this is Phil Charles from the UK. Yeah, my question really is about whether you and perhaps Mark have anything on the development plans for the coming decade or so in the area of the resolution that's being achieved with the X-ray missions. I ask that because, of course, we are all aware that Chandra is aging and it has the finest angular resolution we've ever achieved. And is this an area that is receiving attention, given that at every other wavelength, we go to better resolution, angular resolution as we go forward? Would you like to comment on that?
Yes, so I am not an absolute expert in X-ray astronomy, so I might not be completely the best person to answer this. But if I look at New Athena, I think this is definitely the next big thing in X-ray, and I think we are exceeding the resolution. Even with our D-scope that we did from Athena, I think we are still absolutely amazing with this telescope. So I think that would be the answer to that from me.
So just to answer Phil's question, we're making a number of investments in X-ray mirror technology at NASA, at Marshall, and at Goddard. And I'll just mention one, which is at Goddard. They're working on developing very lightweight silicon X-ray mirrors, which will give you both a much larger collecting area for a given mass compared to glass, for instance. And they also have the promise of improved angular resolution.
Thanks. So in the spirit of moving things along, let's thank Nora again. Our next speaker is going to be Noriko Yamasaki, Director of Astrophysics at ESAS JAXA. And so when we can get his
Can you hear me?
image and sound and his slides, we'll turn it over.
Okay.
Your slides. I'm sorry. Thank you. Slides.
I'm Noriko Yamasaki from ISAS, Institute of Space and Astronautical Science. As a director of the Department of Space Astronomy and Astrophysics, I will introduce ISAS program in global coordination of ground and space astronomy. I'm sorry that I cannot attend the IAU General Assembly in person, I hope that you can hear me well, and if you have some trouble, please let me know soon.
It's good. We can hear you very well.
Okay, so please go to the next page. Yes. So here I show recent ISAS missions to study astronomy, astrophysics, and planetary science. Now the boundaries between them are getting blurred. Some are observing astrophysical objects, some are observing planets and studying the evolution of solar system, and some are studying both. You know that Hayabusa and Hayabusa 2 are sample return missions from asteroids, and Hinode is observing our sun. And Kaguya observed the moon, and Akatsuki went close to the Venus. Isaki was designed to observe planets like Venus, but also used to observe astrophysical objects like clusters of galaxies in UV. They are all designed, developed, and launched by ISAS. So, next page, please. Yes. So, the ISAS is a part of JAXA, Japan Aerospace and Exploration Agency, and focuses on the space science from pure science and engineering aspects. Our missions are generally categorized into three by cost and launch method and strategies. Our largest class missions are launched by the Japanese H2A or H3 rockets. They are defined as our flagship. And the concept might be proposed by science communities, but chosen by a strategic point by ISAS. On the other hand, the medium-class missions, which are launched by the Epsilon solid fuel rockets, are proposed and selected competitively by the bottom-up process. The weight and cost of satellites or surveyors are limited in this class, but we aim to launch them more frequently than the large class missions. And there are various small-scale projects performed by ISAS, utilize various occasions for space science, such as balloon-borne experience, sounding rockets, and the International Space Stations. And also it includes the contribution to the international missions as a junior partner. So go to next page, please. Yes. Okay. So here's our recent and future roadmap of ISAS space science and exploration project. Last year, we launched Prism and SLIM by the same H3 rocket. SLIM was originally designed to be launched by the Epsilon, but changed to be optimized to launch schedule. Our next L-class mission is the MMX, the Martian Moon exploration, and followed by the right part. For the medium class mission, Destiny Plus has both engineering and science perspectives for deep space exploration. And Sorashi and Jasmine have selected and promoted to development phase. And the participating in international missions are listed at the bottom. The hardware to Jude, Hera, and Roman have been delivered, and the contribution to the Comet Interceptor, Ariel, and Dragonfly are being prepared. Next, please. Yes. So I'm really happy to introduce you the Prism as a good example of a successful global coordination. Prism was launched in last September and now observing the celestial object every day with X-ray microcalorimeter array. This is the first press release data of the supernova remnant N132D measured by the resolve. You can see many emission lines from the spectrum, but the line width is slightly broadened by its internal velocity. So please go to the next page. Yes, okay. And this is the energy spectrum from the other supernova remnant, W49b, analyzed by Sawada-san. It is not yet published, so please do not take picture of this spectrum. The line widths and the intensity patterns are quite different from that of the N132D. So you can see that the X-ray spectroscopy is entering a new era with prism. And unfortunately, as you know, the gate valve of the resolve is still closed, but we will try it again at appropriate time. And very happily, the life of the liquid helium is estimated to be almost 6 years, twice the requirement due to the very small heat loss inside the cluster. Go to the next one. Collaboration in PRISM. PRISM is built by the collaboration with NASA and ESA. The calorimeter array on the detector assembly and X-ray mirrors are delivered from NASA, and the filter foil with calibration sources are developed by Epsilon and delivered by ESA. ISAS and many university scientists and contractors involved in the mission. And ISAS developed the cryogenic system and also the satellite bus system. So there are many parties to realize the PRISM. So please go to the next page. Yes. So the development was really done in global coordination, even under the spread of the COVID-19. The components and subsystems were developed and fabricated and tested in NASA site and ESRO site and many premises in Japan, and delivered to the JAXA Tsukuba Space Center for final assembly and verification process. This is a very complicated one, but it was necessary. So please go to the next page. So this is a really good and successful example of the global collaboration in IHAS. This is not only accepting the deliverable from components from abroad. The collaboration starts from the planning, design, and ARB on ground and in space. And right picture was taken in last October in NASA's operation room to celebrate the first cool down and performance verification of the resolve calorimeter in space. The scientists and engineers from ISAS universities, Goddard and Esron and contractors work together very closely. And I want to mention our deep appreciation to the NASA and ESA colleagues that they decided to contribute to the PRISM even after the tragic failure of the Hitomi in 2016. And I also mentioned that this is supported by the science community. This year we called the guest observing program after the performance verification phase, and the time allocation is 48% for JAXA and 44% for NASA and 8% for ESA. And the oversubscription rate for the allocated time is 6 ± 1 in all 3 regions. So the interest to the scientific observation and effort are well balanced. That is very happy thing. So please go to the next page. Yes. Okay. Another example of the coming global coordination is a contribution from ISAS to the Roman telescope, which will be launched in 2025, I hope. And ISAS supplied optical components for the chronograph, such as prism and lenses. Also, we will supply the K-band communication link by JAXA's 54 meters antenna. This link will serve complementary coverage for the Roman telescope. And also, the coordinated observation by Subaru telescope is planned and will be implemented by Subaru user committee. We hope that this will be a very nice example of the coordination of ground and space astronomy. So next page, please.
I will lend Noriko 5 minutes.
Okay. This is the last page, so it's okay. And so this is the current summary and the way forward of future missions. And ISAS has now 3 ways of space science missions, and all 3 categories can use the global coordination. And collaboration of ground and space telescope are also being planned in many aspects. It can be follow-up observations and multi-wavelength coverage, as I used before, and I hope multi-messenger astrophysics will come soon, and collaboration by ground segment will also play an important role. And in ISAS, we have started to discuss to review the cost caps of ISAS space missions to cope with the very rapid inflation of space instruments. However, that the scale of the space mission is growing, such as proposed HWO. So in parallel with the discussion among scientists, ISAS has started the discussion to use aircraft slot to international collaboration. This is the way to prepare for the larger class international contributions. And I know that global coordination will be formalized for many reasons: scientific and technical, financial, programmatic, and political reasons. But I want to emphasize that this shall be defined based on the major discussion communication between science. And yes, this is very essential, and this is what we learn from our experience. Thank you for your attention. So that's all.
Thank you very much. Are there questions for Noriko? Okay, a microphone is traveling. Hang on just a sec.
So thank you very much for this presentation. This is Evine van Nishoek talking here. I was wondering whether you could say a couple of words on JAXA's plans now for the far infrared in space missions.
The far infrared, yes, the Hisaki was planned to use for the planetary science in UV, but now some group thinking about to say upgrade it to the astrophysical observation by it is called as a Laputa. And then we are thinking to say contribute this technology to the HW if possible. So this kind of technology is very continuous and it will cover the planetary science and also the astrophysical observations.
Other questions? And people online are encouraged to ask as well, and we'll keep an eye out for you. Okay, if not for now, let us thank Noriko again. And our next speaker, whom you see, is Hu Zhan, and he's from the Chinese Academy of Sciences. He's the PI on the Shunqian mission, and he's going to tell us about that specific mission. So when slides are up, You can go ahead, Hu.
All right, thank you very much for the opportunity to introduce the Xingtian mission. It's a major science project of China Manned Space Program. It started with the concept of a telescope mounted on the China Space Station. So it's also known as the China Space Station Telescope. We still use the name China Space Station Telescope. Next page, please. So it's essentially a serviceable 2-meter wide-field space telescope co-orbiting with the China Space Station. The space station is called Tiangong, and when the telescope is docked with the space station, just like the artist's rendition on the lower left corner, the telescope can be serviced, can have upgrades of instruments and repairment, just like Hubble Space Telescope did. It will be launched with 5 first-generation instruments, including the survey camera, terahertz spectrometer, a multi-channel imager, an integral field spectrograph, a coplanet imaging coronagraph. The main mission is to carry out a wide area multi-band imaging and a slitted spectroscopy survey. It will take about 7 years. And then we will also carry out other key programs and the geo programs. That will take about 2+ years. And being a survey-oriented project, can cover a very wide range of science. Next page, please. Next page. Extragalactic science will be the major science drive for CSST. In particular, you will see later the telescope has an off-axis design, so the PSF will not have the diffraction patterns from secondary mirror support. That means the PSF will be round, very friendly for weak lensing studies. And of course, it will cover more than just cosmology. It covers all the way, from the remote galaxies to nearby galaxies, stars, solar system, and also exoplanets. Next page, please. So the survey will cover 17,005 square degrees in imaging in 7 bands. It will also cover the near UV part. It's a very unique among surveys of its time. And the 5 sigma point source limiting magnitude for G band will be 26 magnitude. The slitted spectroscopy survey will cover the same area and same wavelength. The spectral resolution will be on average above 200. And we also have deep component and also an extra deep component from the multi-channel imager. It will reach a V-band of 30 magnitude, covering 300 square arc-minute. The lower left, we have a demonstration, just a demonstration for the survey coverage. The red dots are deep fields, just for demonstration only. And we will select the fields next in 2 years. Okay. The lower right figure is from the kids team. The vertical axis is the area, horizontal axis the number density of galaxies. That's extremely important for cosmological surveys, especially for weak lensing studies. The number density, surface number density of galaxies will be very important for shear measurement. As you can see, we can divide current ongoing surveys, past surveys, and the future surveys into different categories. CSST and LSST, Euclid, and Roman will be they are all 4-stage dark energy surveys. I would say that CSST is very competitive, but at the same time, its observations will be also very complementary to other projects. Next page, please. So the telescope adopts a Cook-type off-axis 3-mirror nesting design. The primary is made of silicon carbide. The PSF will have a radius encircling 80% of energy of less than 0.15 arc-second. That includes the optical system as well as all the perturbation, jitter, and so on. The field of view for the survey is 1.1 square degrees. Actually, we use 1.1 square degrees, and the pointing is controlled by control momentum gyro with a Stewart platform plus fast steering mirror. And you can see that the MCI, the multi-channel imager, the integral field spectrograph, and the coronagraph are on one side of the telescope.
Who, we've lost your sound here.
Error, a different field of the optical system for the qualification model. Basically, the MCI, IFS, and terahertz spectrometer have already been integrated with the optical system. They are under test now. The survey camera and CPAC are slightly behind schedule, but will be ready next month. Next page, please.
I'll do it, and you have about 3.5 minutes.
Okay, okay. Next page, please. So the survey camera, I just skipped the details, but we estimate the depth with all the efficiencies, transmissions, and so on. We can reach G-band 26 magnitude, and in other bands around 25 magnitudes. And GU, GV, GI are the grating bands. Next page, please. These are the some tests on the qualification model of the survey camera, and we see the filter and grating assembly. We see the focal plane. Part of the focal plane is populated with mechanical models, and we have about 20 devices that can take real images in the qualification model. The flatness is about 25 microns. And on the right side, we have filter transmission curves and also the crosstalk test on the CCD. Next page. Here is an example of the GU grating test. On the left, we have we use monochromatic light to test the spectral, to measure the spectral resolution, and then the figures at the top row on the right side, we have the throughput of the gratings, actually plus filters. Okay, they all meet the specification, and the spectral resolution is above 200. However, you can see that spectral resolution is not that uniform. It changes with wavelength and also changes with the field of view. Next page, please. This is a test of the terahertz spectrometer. It covers a frequency of 0.41 terahertz to 0.51 terahertz with a bandwidth of 2 gigahertz, spectral resolution of 100 kilohertz. It will study the molecular clouds, carbon cycling in the galaxy, and will do a deep spectral line survey as well. Okay, next page, please. This is multi-channel imager. Basically, it split light into 3 parts: the near ultraviolet, the red part of the visible, and the green part of the visible. In each part, it has 10 filters. One of the tasks is to do the extra deep field of about 300 arc square arc minute. And the other is to do very precise calibration, photometry calibration for the survey camera. Next page, please. This is the integral field spectrograph. It has a field of view of 6 arc seconds, and it's divided into 32 by 32 pieces, and each piece will be dispersed, and spectrum will be taken. The resolution, spectral resolution, will be greater than 1,000. It will be used to study supermassive black holes in galaxies, star formation in galaxies, and also strong lens galaxies. Next page, please. This is a critical piece of component, the image slicer. It's very small, has to be manufactured piece by piece and glue them together. It's a very difficult to make. And on the right side, we see the qualification model of the IFS. It's in the vacuum chamber for test. On the lower right side, I believe that's the red channel test of the spectrograph. Next page, please.
Will do, and it's time to wrap up.
Okay. So this is the last instrument, the chronograph. It aims to look at cool planets. Okay, more mature. Planets around more mature star, not Earth-like, but still we are trying to reach this region in this figure. On the lower right, that's a test of the qualification model. It reached 10⁻⁸ contrast within 0.2 arc second. Last page, next page, please. So let me just stop here. This is a photo taken at the science meeting last year. We much welcome collaborations. Okay, thank you very much.
Thank you. A quick question specific for who and his mission. Microphone is coming. Hang on.
Thanks a lot for that. Could you say a little bit about timelines, not just launch, but for the instruments themselves? When are they likely to be fully integrated?
Next month, we will have all the 5 instruments ready. They are qualification models. So after that, they will be integrated with actually only 2 left, the survey camera and the chronograph. Next year, the test will be run until mid next year. So we will finish the whole telescope, the qualification model of the whole telescope, and then we enter into the flight model production. We expect to deliver the whole telescope, the flight model of telescope, by the end of 2026.
Any other questions? Let's then thank Hu again for.
Thank you.
And now we'll see what we can do about having a hybrid panel and as natural as possible a discussion. So I will kick off with a question, but I encourage you to think about the questions you want to hear from folks. And so let me ask, and we'll just ask the panelists to jump in. I'm not going to point at anybody. So what technologies do you think are most needed to be developed for next generation instruments? So you get some seconds to think, but then go ahead, Mark.
So I I will say for habitable worlds, we're obviously focusing on achieving contrasts down to 10 to the -10, which means we're needing to focus on ultra stable. But one of the things we'll be doing at NASA next year is having a workshop for emerging technologies, and we want to take a serious look at what we should be doing in quantum, metamaterials, application of AI to technology rather than big data. And if you're wondering what that means, for instance, use of AI for robotic servicing, wavefront sensing and control. So we're trying to, and integrated photonics is another one. So I think there are a lot of technologies out there that we're not really looking at closely enough right now. So from a NAV's perspective, that's what we want to do.
Other perspectives?
Yeah, I could add from the ESA perspective, especially if we look at solar system exploration going further to planets further away, we need to look at new propulsion systems to do that. And for Europe, we're thinking especially about nuclear power. That is something that we haven't had the chance to develop to this point yet, that we can use it, for example, for L4, but it's something we should look at in the future. Other things is really miniaturizing technologies that we already have on Earth and make them space ready, right? Such as cold atom interferometry to get really accurate clocks in space, to do experiments on general relativity, and also for gravitational wave detectors. X-ray interferometry is another really interesting thing to do, right? It's very challenging with those very short wavelengths, but doing X-ray interferometry in space would give us an angular resolution that would be insane, right? So I think that those are things. AI in space is also definitely something we're thinking about. Those are just some ideas from our side.
Any other thought? Go ahead.
So I'll just add one thing. I think one area that's really interesting is quantum. And you have the opportunity to do super resolution with quantum. And the example I always give, which is a bit blue sky, but Hubble resolution in a CubeSat. There's also quantum metrology, which offers the opportunity of doing absolute calibration rather than relative. So there's a lot of new ideas in quantum physics that we should be using in astrophysics.
Other thoughts from our panelists about technologies you would like to see? From the room, from online. Did they hit everything you were thinking of?
What about cryogenic sample return of icy moons that was originally planned for Voyage 50 from ESA?
Yes, that's definitely up on our list. I haven't mentioned all of our new technologies that we are listed in Voyage 2050, but cryogenic sample return is one of them.
And what is the status of these studies?
Well, it's currently not planned for the next big L mission, right? Because we are not doing sample return for L4, but we will be looking at this in studies and hopefully developing this for our next big missions that go in that direction. So it is not yet really in the status that we can do it, but we are working on it.
Thanks.
Any other thoughts about tech development that would be exciting and or needed? Okay. Anyone in the audience, have you been thinking of questions for these folks? Okay, hang on.
Thank you, and apologies for not introducing myself earlier. Nancy Levinson, Space Telescope Science Institute. I'm particularly interested in Habitable Worlds Observatory, and so we heard from Mark about some of the NASA perspectives, and I'd be interested in hearing about some of the international perspectives on collaboration in that, and also in the theme of this whole session of some of the ground observing opportunities as well.
So I think that's really a question for ESA and JAXA, right?
Yeah, I mean, I can start. We are absolutely, of course, absolutely very interested in the HWO, and we were happy to collaborate on that. I cannot really speak about all of the future collaborations because that is not my place here. But we are also looking already for search for exoplanets for our next L missions. As one of the topics was look for tempered exoplanets. So we are not going to copy HWO, but we are probably going to try to complement those kind of missions because looking for habitable worlds is really one of our biggest questions, right? And I think there's definitely room for collaboration, but also for complementing this mission on our side.
And I said I wouldn't make pressure, but Noriko, do you wish to comment?
Yes. In ISAS, of course, we are discussing about the HWO, and we sent to delegate to the HW staff team, and they are discussing with the many ISAS people, and also for our flagship mission, we have started to think about the next flagship mission, but there are several candidates about they are from very wide field that X-rays and infrared and sample return and etc. So it's not yet decided, but there are many options we have.
Any other thoughts on that question? Saknikte online, would you like to unmute and ask your question?
Hi, good morning. Can you hear me?
Yes, we can.
Yes. Hi, my name is Sak Medina. Very nice and very interesting talks from everyone. Well, I think my question is a little bit about the not political, but like the social situation of how touristic space is going and growing. So I wonder if the space agencies have specific plans to stop or prevent the touristic space troubles and focus on the scientific research and not only in commercial or touristic stuff. Is it clear, my question?
Very, and you asked the agencies, and then I might make an editorial comment.
So I would just say that NASA has a very specific mission. Part of that is Artemis, which is the return to the moon, and there is no space tourism element to that. And NASA continues to invest in a very broad and diverse space science program. And we don't dictate to the commercial world what they should be doing outside of our agency.
Yeah, I can basically say the same for ESA as well, right? We are not going to interfere with what private sector will be doing. We are working with the private sector already with launches of SpaceX, but what they are doing in terms of tourism, I think personally, I think it's really cool. I really would encourage science like space tourism because it's like the exploration and it's always gets the interest of the public, right? If you have something like this, but it's not something we have anything to do with, at least of now.
Yes, and situation is almost same in the JAXA and ISA. ISA is specific to the science mission, and the JAXA is a general space development. But we do not think about the space tourism, but we will say help the many companies in Japan for the space development.
In CPS days last week, we talked about the fact that the dominant use of space has shifted from space agency exploration to commercial use of low Earth orbit. And so the assurance of non-interference now rests with the licensing agencies in each country that launches the space tourism experiences. And our job as astronomers is just to make sure that it minimally interferes with our ability to make our observations and launch our missions. So we need an advocacy voice, but the agencies don't control that traffic anymore. Okay, Joe had a question, so.
Okay. Joseph Lazio, Jet Propulsion Laboratory, Caltech. Mark, you alluded a bit to TDAM. So in the spirit of the session, TDAM, time domain and multi-messenger astronomy, what discussions are going on or what thoughts have been given in science working groups to something like an electromagnetic counterpart to a LISA source that somebody wants to follow up with UVEX or CRISM or some other asset of another space agency?
So I would certainly say from the NASA perspective, from NASA Astrophysics, we are not looking at specific TDAM missions, but we have a number of smaller opportunities within the RNA program. We have a SMEX opportunity coming up and a MIDEX later this decade. And of course, we're in the process of reviewing probes. So all of those have either already had or there is the opportunity for a PI to bring such a mission to the table and propose it.
I think this is also a great question for probably the session tomorrow on multi-messenger. But I wanted to say I just recently had a discussion with astronomers at the conference for LISA for really follow-up of like instruments. And we were also talking about instruments on the ground, like for ESO, for the ELT. And I think this is really something I would love to open the conversation to have instruments that we can use to do LISA follow-up observations. But from the ESA side specifically, I couldn't think of something that we have in the pipeline right now.
Any other thoughts?
I think on the ground there will be a lot of time domain projects. Even in China, I know at least 2 or 3 large field of view wide field telescopes. They are focusing on time domain studies. So I guess it will be telescopes at least on the ground for the follow-up. In space for CSST, we actually we have a sufficiently large field of view and quite a few instruments on board. If we have good alerts, and we can certainly arrange certain follow-up observations with our instruments. Even right now, we have in China, we launched a soft X-ray telescope, wide field telescope. It's called Einstein Probe. And I think there will be other telescopes, space telescopes, launched in China in the next 5-10 years, right?
Other thoughts about a preview of time domain?
And I want to mention about the CRISM, that the CRISM is always accept the TO observations. And actually, we observed one supernova already. And but it is not designed to say for the very rapid commanding scheme. So maybe in the multi-messenger era, we need to design the communication link for the satellite in a very special way, I think.
All right, well, another question, which is sort of like, which of your children do you love the best? But what do you see as the most promising discovery areas that are now in planning for future and far future missions? Where do you think the payoff's going to be?
Okay, well, I'll go. I think we haven't finished yet with Webb and seeing some of the science that Webb couldn't do. So I think some of the early universe results that are going to come from Webb over the next 3 or 4 years will be really exciting. And I do think that both the search for life in the universe, in the longer term with the Habitable Worlds Observatory is obviously going to be a really major payoff. In the nearer term, I think just new science from the time domain and multi-messenger as all these new resources come online, Rubin, and then being able to do follow-ups with both our larger missions in the NASA portfolio and a lot of the smaller ones. Many of those CubeSats and small missions that we're looking at on that fleet chart I showed are actually designed to do TDAM science already.
Yeah, and I have to add, I really have to add gravitational waves to this, because I think this is going to be something in the decently near future, and having a new window into our universe with like a completely new messenger that we've seen on the ground, but not in this frequency domain. I think it's going to be absolutely amazing to really see the big events, the supermassive black holes merging, and maybe many, many other things that we couldn't foresee with observatories such as LISA, but also more advanced ground-based observatories. It's going to be very exciting.
Okay, one last curveball just like that. Oh, please go ahead.
Sorry, that I agree with Nora that the new discovery will not be limited in space science, but will be done in the coordination between the ground and space astronomy. And personally, I hope that we need to find or define that dark matter and dark energy in next several decades, I hope.
So one last thought. Do you think the current process where there's lots of communication and competitive choices and strategic choices is enough to avoid duplication of effort and get a complementary suite of instruments into orbit, no matter whose they are?
So I will say yes. I think that's true. As I said, we work very closely with our international partners, so we're always coordinating, with regular discussions. I talk pretty much every month with JAXA, with ESA, with the Canadian Space Agency, for example. So we are always, coordinating and trying to make sure that we're, working with a broad portfolio. And I'll also just, say positive things about the national academies. I think they do a great job of making sure that we avoid complete chaos by really laying out, a plan of action for the decade, certainly for NASA, that we can follow and work with our stakeholders on the Hill as far as the funding aspect goes. So yes, and we also have these ad hoc international working groups like the one we've set up for TDAM science, which also help avoid everybody building the same mission.
Yeah, I would absolutely agree. I mean, we are also so connected nowadays. We're not doing things in isolation anymore, right? Most of our missions are in collaborations with our international partners, and we also need to justify our missions. And if there's the same mission happening with a different country or continent, our community will say, no, we are not doing this, right? They hold us accountable for this. And I think that really gives us also a good check to not duplicate missions and to rather collaborate and make them complementary.
Yeah, I think we benefit from studies from other countries, and we try to avoid the duplication of the projects. And certainly, I think in the future, we certainly from myself, I hope we can have more direct discussions with colleagues at ESA, in NASA, in JAXA, and other countries. Right.
I also agree about that idea, that because say that the demand from scientists is growing, and always the cost is limited. So the coordination global coordination will be very efficient. So I really agree about that.
That's great. Well, we have come to the top of the hour, and I think we should be exceedingly grateful to the agency people who have joined us from around the world. And so let's give them all a great thank you. And we reconvene at 1:30 for the next session. So I'll see you then. Yeah, and so
And I'll just ask him to question what my instinct is just to take one from the floor first. Yeah. And then just Joel turn. Yeah. If there's anybody there. Yeah. And this is the thing that so we won't need that. For the rest of it. I think the only person I don't know is so hugely I've seen everybody else.
very good. Yeah, I think 10 years is, I think 9 and a bit. Good for you, it's good for them. Big fan of Senegal. We have 3 Used to be 80 dollars, and now it's 800.
Or the aim of this? Okay. Okay. We won't start right, so there's this little toy here. And when you're slightly, yeah, exactly. So you just need to advance your aim.
Talk to this microphone, but not too close like most people? Yeah? Okay. Okay, great. And I presume this will give me the presenter mode, right? See the next slide?
Yes,
Yeah, and if it doesn't matter. Okay. Right. Okay.
And there was a panel just before that meeting, and Roger was the chair of that panel, and that panel came back and said, this is way too expensive. You will never be able to pay for a 100-meter telescope. And the number was 1.2 billion units. Well, I can't remember if it's dollars or euros, but that was the number at the time. And here we are spending more than that on smaller telescopes. So I'm going to give you an update. This is really slides that I've put together from Michele Cirasvolo, who used to be the ELT program scientist, and also Roberto Tamai, who's the ELT program manager. So this is a picture from June. This is, you can tell a telescope is under construction because the lights are on. That's very typical. So all I'm going to tell you is available on websites, at ESA websites, and I'm just pointing you to this website, which was redone last year, elt.esa.org. And so everything you don't understand what I say, you may find there. All the pictures and videos that I'm showing you are coming from that website. This is just a recap to briefly tell you how this telescope it has a bit of a special optics, and so I wanted to tell you this. So you have, this looks like any other alt-azimuth telescope that you may know. It has, in this case, a segmented primary mirror. As I show you, the beam goes through 5 mirrors. And this is the official first light. Let's agree that we want to be observing by the end of the decade in regular operations, whatever the end of the decade means. So this is showing you the beam as it goes through from the primary up to the secondary, then through a hole in the quaternary mirror, down to the tertiary mirror, up to the 4th mirror, and then down to M5. M4 and M5 are active mirrors so that they can do the active and adaptive optic that we need. So you see it's a rather complicated beam that we have here, but that should give us a good image quality. Just for scale, the secondary sits at 65 meters above ground, okay? We'll see that a little later. I also like this picture because in the background you see Paranal. Okay, so that's another nice. So these are a couple of images from June, from about 3 or 4 weeks ago. You see the cladding is going on to the dome. In some sense, the dome is never going to look as nice any longer. You know, I'll show you the see-through image a little later. But so the cladding is going on. Here's a picture from the top down, and you see how the cell, the M1 cell support structure is coming together in there as well. The dome, by the way, has been moved by 10 meters one way and then 10 meters back. It's described as a manual move, but it took several machines to do that. So maybe it moves. This is a picture from the inside. You see parts of the M1 structure. What you can't see is on the right side, there's the first part of the Naismith platform that's going to come up. On the opposite side, they're still working on this. It's a big stadium in the end, if you look at that, except that everything moves. So I'd give you an update on the various optical systems that we're working on. We just had the last blank of the M1 mirror delivered by Schott. So that was at the end of July. We now have 949 blanks. Some of those are spares. I think we have, I don't know the exact numbers, but there's a few spare blanks. I don't know what they want to do with this. What you see in the picture is the hexagons. So they're cast as round blanks. They're then shipped to Paris for the polishing. And the first thing they do in Paris, they cut it up into the hexagons that are needed, and then they're polished. The M1 support is coming from the Netherlands. So you see that in the second picture from the top. That's the support of the individual segments. Those are also almost all delivered. So there's going to be 936 of those, and we have 95 of those accepted. And the fixed frames, this is the bottom. You see the storage of those fixed frames. They're all coming to Chile. The So I'll say something about the M1 maybe later. The M2 mirror is a rather complex mirror because it's convex, and so that means it's going to be difficult to actually measure. The polishing is really making good progress. They're now at 60 nanometers RMS across the mirror, and it should be finished rather soon. The M3 is just a folding mirror, so it's really the easiest mirror of all. That is in the grinding process. That's a rather relaxed schedule on that one. The other mirrors are more complicated. And then we have the cells that hold these mirrors all in verification right now at the various sites in Europe. This is a picture of the backplate of the M4 mirror. So that's a 2.4 meter diameter mirror. It's active. It has, as it says here, over 5,000 actuators to do the adaptive optics. It's very similar to what Pat just showed. So this is a 2.5 meter mirror that's just under 2 millimeter thick. It's crazy what people do these days. So that's the blank on the right side, the shell that you see on the right side, and this is the back plate of that mirror, and the holes are the actuators that are going to go through and form the shape of the M4 actively. And this is the M5. This was a big worry, and it still has lots of people worried. So this is a silicon carbide blank, 2.7 times 2.3 meters. The blank is finished, and you see this is made up of 6 segments that are bonded together. There are concerns how to polish such a large silicon carbide mirror. I think that's the largest mirror that ever is going to be polished. There are some small blemishes that we have, and so there's some nervousness that we get this right. So to fix the problem that this may not be ready at first light, we actually get a glass mirror from Schott as a backup, which will reduce the field of view, but at least we will be able to start with the telescope. Here's a sort of a summary of the instruments that we're looking at. There's 3, 4. If you want what we call first light images, they're not all for first light, but this is 3 images that we want to have at the very beginning. There is Mikado, which is an imager, and it says it there from 0.8 to 2.5 microns with 2 magnifications, and it also will include a single slit spectrograph. The Mikado will be supported with an MCAO module, which is separate, Morpheo, so that's built separately in front, that should go in front of Mikado, and that started a little later, and it's going to come in a little later, so we're thinking in 2031 or 32. Then we have METIS, which is the thermal infrared imager, so L, M, and N band, so 3, 5, and 10 microns. That's a single slit spectrograph, and it will also include an integral field unit. The METIS at the moment and Mikado are sort of competing which of the 2 instruments is going to be first at the telescope. So the timescale is quite good. METIS has finished its final design review. We will issue a press release, I think next month, about Mikado also passing its final design reviews. And the last instrument that goes in is Harmony, which is a hugely complicated instrument. Will be an IFU from the optical, the visible, into out to 2.5 microns with a resolution of 3.5 to 20,000 itself, and it will have also 3 magnifications. Harmony is going to be a little later. It also includes laser tomography, AO. And there's 2 more instruments that are already planned. We actually signed a contract for Andes to start developing the design, finalizing the design. That's going to be high resolution spectrograph in the optical. There's a bit of a worry that the telescope may actually not yield the specifications for the optical image design. So we still have lots of worries that we're thinking about and we need to work on. But that's an instrument that's going to come in at a resolution of over 100,000. I don't know if some of you remember Codex. That was sort of a precursor proposal for Andes. And Mosaic is a multi-object spectrograph, and that's supposed to come together so that the proposal is in. We're having a number of reviews to make sure that we understand everything is working okay. So those instruments, we would argue, will come in 2030, in the mid-2030s, I would say. Okay. This is just to give you an idea about the wavelength coverage and the spectroscopic power. So you see the different magnifications in harmony, the Mikado slit, the wavelength range. So it's just covering the usual thing. What I would like to point out, which I haven't done here, is we of course have the equivalent for the 8-meter telescopes as well. So for ESO and for our community, we actually can offer this in addition to the 8-meter telescopes that we already operate. So I wanted, this is why, this image, you can't take this image anymore because now the cladding is coming on and it's not as beautiful. So the trick is, the trick is that we of course have the same image from the VLT, and I let it to you to work out which one is sunrise and which one is sunset. So to finish off, so what's happening around Paranal is actually quite amazing, I find. I call this an astronomy science park. We have Paranal at the bottom with the VLT and the Vista is right there on the next hill. And then we have Armazones, where the ELT is being built. And in between, in the next few years, we're going to host the Cherenkov telescope array, the southern array, at the same place. So that's actually coming together quite nicely. We also, of course, I don't want to forget about this, we have ALMA that we're operating. This is about 500 kilometers to the north. And we still operate La Silla, which is 600 kilometers to the south. So that's the situation that we have. We're quite optimistic that we're going to get things done. So what I have here is just a sort of a drone flyover, and I'm taking questions while you can watch this. This is just the situation in May, I think, as it is. We do see changes every month in the telescope structure right now. Thank you.
Thank you, Bruno. Thank you both speakers for keeping very well to time. So questions for Bruno, just clarification questions now, specific things. Carl. Oh, do you want to, can we get you a microphone or do we use this one? Maybe you use this one. So say who you are and speak into the microphone.
It's Carl Glazebrook from Swinburne. So clearly the telescope is being put together. What about the first instruments? Have they started cutting metal yet?
So they're just starting to cut metal. I mean, they passed FDR, which is the end of the design phase, and now they're starting construction. So yeah, it's true. I mean, telescope and instrument, there's an interesting time scale. We may have a situation that we will run the telescope for maybe a few months with what's called the phasing and diagnostic station, which in the old days would have been called the test camera.
So there's a couple of questions over here, so we'll do the one and then.
Phil Charles, UK. Fantastic, of course. I hadn't realized looking at those overviews of the instruments. Does harmony really only start at 0.5 microns?
That's right, yeah.
So but Andes will eventually get you down shorter. Yeah. I say that because I've recently been working with some fabulous VLT X-shooter spectra at 3,100 angstrom. This site has staggering throughput there, and the thought of what ELT could do between 0.3 and 0.5 is astonishing. Well, I'm just a comment.
Well, no, you're absolutely right. The problem is your beam size grows with the telescope size. And so if you can't do the adaptive optics to get your beam down, you build gigantic instruments, and that's why we're staying away from the bluest wavelengths. There is also, I mean, there's an interesting thing that people kind of forget. The diffraction limit of the 8 meters and in the blue is exactly the same as the diffraction limit of the 40 meter at K. Okay, so there's a great synergy between VLT and ELT in terms of that aspect. There's nothing that prevents the community to later develop instruments into the further blue. Yeah.
Okay, thank you. So let's just say now, these are probably specific to the ELT, but of course we do have an extended period to discuss the topics more generally. So let's take Beth first.
Beth Willman here. In the spirit of sense of scale, about how many meters tall is that red and white crane?
Oh, so once the shutters go in, the top of the telescope, the top of the dome will be 80 meters, to give you an idea. Okay, so I think the top of the dome as it is right now is 65 some meters, maybe a little more. The crane must be 120, 130. It's a 600-ton crane. I have no idea how they got it up the mountain. It's
in small pieces, I think.
Well, there was a statement that it may be the biggest crane in South America right now.
Seems likely. Now, is there anything online? Any comments or questions online? Not yet. Okay. Richard.
Hi, Richard Green.
Yeah.
Since you mentioned it, are you willing to elaborate on what the current concerns are about delivered image quality?
Well, so we have 800 segments that we need to phase, and there's people working on this right now. This is a non-trivial problem, and what's not quite clear, but it turns out the primary mirror has 6 identical segments if around, and these segments are separated by a shadow of the spider. And I'm told, I know nothing about this, but I'm told that one of the biggest issues that they have right now is if there's a piston offset between segments behind that shadow, they need to find out how to actually correct that. And so there's ideas, and they're all working on this, but those are issues that we're dealing with right now. I didn't tell you the number of edge sensors and things like that. It's a huge undertaking to get that mirror just correct. I mentioned the M5 mirror. That's one of the issues that we're worried about. So yeah, but in some sense, the M4 is comparable. It's bigger, but it's something that we've done on the VLT. So that's technology that we kind of know, and the company who's dealing with this knows about this. The M5 is sort of a bigger issue.
Okay, just to remind you, I'd like to broaden out the discussion to both US and European projects, but let's take one more question here.
Thank you, Bruno, for this really impressive talk. One thing, I'm sorry, Peter Habison from ESO Science Outreach, Austria. You didn't talk about the adaptive optics systems so far and about the lasers and everything. So can you say a few more words about that? How is the status, and do you know what's going on?
Yeah,
and will this be operational already at the beginning, or is it planned to have that afterwards?
Yeah, so
because the instruments they rely on that.
Some of them do. Yes.
Oh, some of them, yeah, of course.
So I'm not fully up to speed on the AO system. We're buying the lasers. There's actually, as a matter of fact, there's a bit of a funny thing that some people now say we buy them too early. And there's keen people at the VLT who say, oh, can we use them? So there's a bit of an internal thing going on. I'm not aware of any fundamental issues with the adaptive optics. There's a cost issue with the lasers. So the 8 lasers, the great image that we like to show, we're probably not going to get the 8 lasers at the beginning, but I think they talk about 6 lasers at the moment. So, but sorry, I don't know more about that.
Okay, apparently there's still no questions online, so let me encourage those online to maybe think about that. Any broader questions, maybe to both speakers or specifically to Pat, perhaps? Thank you very much, Bruno. Let's give Bruno. Yeah, other side of the room. Here we go.
Yes, James Lowenthal from Smith College in the States. What thought and planning is going into protecting the darkness of the sites in both cases?
Fortunately, in Hawaii, we're in pretty good shape because we've got a cloud deck that keeps most of the light down. And in fact, if you look at the light pollution map for Hawaii, the dominant source is the volcano. But nonetheless, we're working with the local government there, particularly around airport lighting and things where there's big activity in the parts of the island that are not always under cloud. The bigger risk is in Chile. And as Connie, who's sitting next to you, can tell you, and as you know, it's the advent of LED lighting that is our curse. So we are working now with organizations in Chile. There's a new lighting ordinance that was passed in Chile. I think all the observatories in Chile got together and worked with the government. Key now is, can we actually enforce that ordinance? So, as you know, we're working on it. It's a serious risk. I suspect that you all are probably going to do more of your work in the infrared than the GMT is, and so you're less impacted, but it's a serious issue nonetheless. Yeah.
So it turns out Paranal and also Amazonas are further away from civilization, so we don't have that much of a problem. But there is a road which is turning into, it's a parallel road to the Panamericana, and there's more traffic on that road, and that's a bit of a worry that we have. In some sense, we've been lucky. There was a mine, actually very close where the CTA is now going. There was an open mine that had light, the lights at night, and we were trying to, this is some years ago, and I don't know whether they went bankrupt or it wasn't interesting anymore. It wasn't profitable anymore to mine there, so that went away. But there are, as you say, there's always, we need to be aware that something may happen, and we need to work with the local communities to make sure that they support us. I think in Chile there's quite a good movement to protect the skies in northern Chile because they've realized how important that is.
Thank you. Let's have anybody else? Beth again. Here we go. Okay, we'll take Phil Charles's comment on that point first.
I was just going to say that the absolutely key point in the protection is how the laws are managed. Here in South Africa, because as you know, I was the former SAAO SALT director here, you get a wonderful thing in place like the Astronomy Geographic Advantage Act with its protection of the area around Sutherland and around Carnarvon for the radio, but then you need an agency that can police that, and when things go wrong, that can do something about it and overcome problems when organizations try to get around them. It's an ongoing battle.
Beth Woolman.
Thank you. So one thing I've been struck by over the last week, in a positive way, are the extraordinary efforts related to astronomy for development, from the very small scale, homegrown local efforts to what I've been really impressed hearing from SKA. What's the imperative for these multi-billion-dollar scale projects in terms of balancing the science outcome and the societal outcomes? So I'm interested to hear from Pat and Bruno, what are your thoughts on these multi-billion-dollar projects, the societal imperative, and where do you see as maybe the strengths or the weaknesses in these two huge projects right now in that area?
That's a quick what? I'm going to get up here again. So I spoke yesterday with somebody. So we've done, there's a number of things that are happening and structurally happening. In the agreements that we have with Chile, there's support for local communities, and that applies to ALMA as much as it applies to the VLT, for example. So there's support to financial support to local communities, educational support for schools, for example, in Tal, which is the nearest town. The other aspect is indeed what you say for society. What's the return for society? We do have a program at ESO to really look at that, and there's a brochure. If you come, I hope there's some brochures left at our stand, where actually there's an analysis of what ESO, what the societal impact is. To come back to the other connection in Chile, also structurally there is funding that goes into Chilean astronomy, and outreach every year from all the projects. I think that's true for you as well. And so that is going into this. I talked to a Chilean astronomer. When we started, there were 2 astronomy departments in Chile, and I'm told there's 24 now. So that development of Chilean astronomy has been, it's not entirely, you know, there's been support that they develop themselves and make good use of their natural resource, but there is a continuous support into this structurally through our agreements.
I'll be quick. It's a great question, but I think the key thing that the community wants is not just more astronomy engagement, but jobs, technology development, economic development. And I think both projects and we at NORLAB in Hawaii and in Chile are moving away from the idea where, well, expats come from the US and Chile and do all the really important stuff, and the locals do the basic operations too. Whenever we can hire a Chilean or Hawaiian to do technical work, we do. Chile's economy is growing rapidly. It's now a country where you can get high-tech workers. We invest in them, and so the future really is to have locals at every level of the organization. That's when we really become part of the community, and with the real return then is growth, economic input, and a brighter future for the technical workforce.
Okay, I think I'm going to take the chairman's privilege of having the last question because we should move on. This is a question to Bruno, I think, really. So you gave us a warning at the beginning of your remarks about looking at dates on slides, right? And I'm just thinking, well, it's true that the dates are probably very uncertain, but perhaps the difference between the first light date that we currently think about for EELT and for the 2 US projects is probably that's a little bit more robust than the actual dates themselves. And if that's true, then ESO has an opportunity which you haven't seen for many years, right? And I wondered if the organization has given any thought to how time might be allocated during that period of essentially no competition on this scale, how that might be best used for science, or whether you feel that the best use for science is simply to respond to applications. And I wonder if the organization has thought about that at all.
Yes and no, probably. So there are plans to, first of all, we need to integrate the operations, the ELT operations into the VLT operations, so that there's a lot of thought going into this. We're just starting, we have 4 years to go, so we're just starting to see how the ELT is going to be offered to the community. We have not gone that far that we said, we'll dedicate the telescope to something or specific groups. That's something that we would have to discuss with our committees first, and the community needs to understand what we're doing. So right now, we're literally just starting. I'm talking to my people. It's like, how is the call for proposals going to look like for the ELT? Because hopefully it's going to be the same as for our other telescopes. So in some sense, as I would kind of promote a slogan, ESO has telescopes from 4 to 40 meters. We'll have telescopes from 4 to 40 meters, and you can apply for all of them in one request. My good friend Antoine Meron keeps correcting me. He says it has to say 2 to 200 meters because the interferometry, of course, and he's absolutely correct. So the idea is to, first of all, to offer the ELT the same way we offer, or to offer together with our other telescopes, but we haven't really specifically sort of said this, define key programs or something like that. We have not done that. That's a discussion that we really would have to have with the community because it's important for them.
A quick comment on this issue of the gap between the ELT and the US ELT. There's a lot of hand-wringing in the United States of, oh my gosh, ESO's so far ahead, maybe we should just stop this and do something else. Because remember when Keck was built, and it was 7 years till something else came. When Keck was built, the world didn't say, well, Okay, they've got it. We should all just go do radio astronomy or go, do something else. 11 more 8 to 10 meter telescopes were built. 11 more. So we're, envious and jealous that Europe is so far ahead, but that's not a reason to not do it. There's a vast amount of astronomy to be done and a lot of people to do it. More telescopes means more people. So it's painful you're ahead. Congratulations, but we're not quitting.
That's a good answer, Pat. Thank you. Thank you, Bruno. Let's thank both speakers again. Okay, so it's time to stretch the wavelength range here, move to the radio, and the next speaker is the Director General of the Square Kilometre Array Observatory, Phil Diamond. Oh, you don't. It's not you.
Thank you, Roger, and pleasure to be here. I don't know how many of you were in the session yesterday in which Tony Beasley and I talked about synergies. You'll see some of the same slides, but what I'm hoping to do is give you a bit of a more in-depth tour of the current status of the SKA Observatory and its capabilities. So just to remind you all that we are the newest intergovernmental organization. This is 7 ambassadors and ministers signing the SKA Observatory Treaty at the Ministry of Foreign Affairs in Italy in March 2019. And this was then ratified by the appropriate number of countries in January 2021. So we're about 3.5 years old now. This is our current membership, 11 member states who have ratified the treaty, 2 in the close to the final stages of accession, and others moving up the ladder. And we are also in conversation with a significant number of other countries to extend the membership. And Pat showed a very, very nice map of the world with the various facilities and institutions involved in the US ELT program. And our distribution looks very similar. In fact, it's many of the same countries. And we do sit on all 6 continents. You may notice the tiny little blue speck on the northern coast of South America there. That is our French colleagues. That is a formal part of France. So we'll claim that as we sit on 6 continents. So our mission is to build and operate cutting-edge radio telescopes, but importantly, encapsulated within our mission is that we do intend to deliver benefits to society through collaboration and innovation. So we're building a single observatory which will consist of 2 telescopes across 3 sites. Could somebody close that door, please? Yeah. 2 telescopes and across 3 sites. 1 site here in Australia, in South Africa, another in Australia, and the headquarters in the shadow of the Lovell Telescope at Jodrell Bank. Sites selected very much for radio quietness. They're very low population density. You see the construction cost there and the approximate timelines. Bruno, it's not just optical astronomy that gets the timelines wrong. The history of radio astronomy and SKA is littered with that as well. It is embarrassing, but now we're much more solid on our timelines. So this is an animation of what SKA Mid in South Africa will look like. 197 fully steerable 15-meter class dishes, including 64 from the existing Meerkat, plus the Meerkat extension that is being built now by Soreo, MPG, and ENAF. Frequency range is a mid-frequency range for radio astronomy and 150 kilometer maximum separation. SK Low in Australia, here is the similar animation, very different design, of course, to the telescope. Low log periodic stations, 512 of them, And you can just see this will look like a forest of radio antennas when it's finished. The core especially will look tremendously impressive. Frequency range here is 50 to 350 megahertz. And that 7-to-1 frequency range in a single antenna has been a very challenging target to achieve, but I'm very pleased at the results. So the array configurations are similar. They're two densely populated cores with spiral arms emanating from the core across 150 kilometers in South Africa, 74 kilometers in Australia. And the infrastructure required to support those is impressively large. Hundreds of kilometers of roads, of power cables, of fiber cables, foundations, 103,000 steel meshes for the ground planes for the stations for SK Low. And that's not to mention the hundreds of kilometers of fiber connecting to the supercomputers and the digital signal processors in Perth and Cape Town. And then we're having to rent bandwidth on undersea fiber cables to get to our regional centers. So it's a major undertaking. The data rates are truly impressive. 2 petabits per second of raw data coming from the SK Low antennas, but that gets rapidly reduced. I mean, we're talking 20 to 10 terabits per second flowing through the system, with then data products going to the SK regional centers, 700 petabytes per year. We're setting up this network, this federated network of SK regional centers around the world, which is how the users will interact with the SK data. And all of this is being done to cover a huge range of science. So we'll provide capability in all of these areas of science, which of course I don't have time to touch on. Yeah, thank God for that, Roger. Yeah, I was looking at the clock there as well. In terms of the SKA status, I mentioned this yesterday, we have 300 staff at the moment, ramping up to 450 with the distribution as you see. We have now awarded 3 years into construction, 92 of our construction contracts, 776 million euros of funds committed. And we're looking at early science from the SKA in 2026-27. Just wanted to show you an earned value curve, just to show how we're tracking our plan. So the blue line that you see there is our plan starting from July 2021. I haven't got the very latest data, but you can see there that we're tracking slightly under. So we've spent nominally spent a little bit less than we expected, and we're a little bit behind in terms of the schedule. But actually, we have made advance payments that are not included in the earned value. So if we remove that offset, then the schedule variance is pretty much close to zero, and the cost variance is positive. So I'm really actually pleased with how this is showing that we're tracking the progress. But it's not without its challenges. This is our overall construction strategy and timeline. So our target is to build these 197 dishes and 512 stations, what we call Array Assembly 4. But the council gave us permission to start construction with only about 85% of the funding identified. So we developed what we call a stage delivery plan, which actually delivers all of the infrastructure. It's critical that that is done. And then 144 dishes and 307 stations. And it's my job to be securing the additional funding, which I'm sure I'm very optimistic will come, but it's part of a process in which we're engaged right now. But our intent is to develop the earliest possible working demonstration of the system. and then maintain a continuously working and expanding facility to demonstrate the full performance of the SKA. You see there the critical timelines. AA 0.5, that's an initial 4 dishes and 4 stations. That looks to be on target. In fact, the 2024 July deadline for the 4 stations for SKA Low was achieved. So you can see the timeline unfolding there in that table. So just to give you a bit of a view of, we'll start with SKA Mid, and this is the journey of the first SKA Mid dish from the factory in China. We were tracking it in its 16,000 kilometer journey across South China Sea and the Indian Ocean. The port of Cape Town was congested, so it sat outside Cape Town for about 2 weeks before it would get into the docks. That's Ponso Maruping, the Managing Director of Soreo, and Lindsay Magnus, the SKA Mid Telescope Director. About an 8-hour drive out to the Karoo. That was Tracy Cheetham, who was our construction director, counting all the pieces there. So there's a crew from CTC 54 in China out on the site, actually overseeing the construction of the dishes. It impresses me that they fit in the bolt holes. SKA Mid-dish moving in concert with Meerkat, which was very pleasing to see. So real progress out there on site. This is all supported, of course, by we've had to put in place a construction camp. There's all sorts of activities out there. We have 250 contractors on site building all of our infrastructure, our roads, our low frequency communication system, because there is no mobile phone coverage out there. These are the prototype receiver systems for SKA Mid. The first 4 dishes will all have receiver systems on them. And then across in Australia, it's a parallel process. So on the 7th of March, a heavily photographed first log periodic antenna going in. I actually inserted 2 of the screws in that antenna, so that was a very nice event on a very hot day. Again, we've had to put in place a construction camp out there. There's nothing. This was an empty site before we arrived. It's 14 kilometers from the CSIRO team that are out there. So this is all a brand new construction camp. You see the laydown yards at the bottom right there of all the fiber and power and metal mesh sheets. Alma has its transporter system. We have ours, somewhat simpler. And this is an SKA cluster. We typically have the stations in clusters of 6. And these are the first 2 that are fully populated. This is the core, that's about 1 kilometer across, with an area in the center that the Wadjuri Yamaji Aboriginal people have said is a heritage site, so we're not touching it. There are quite a few of these heritage sites around, which we avoid, and we're able to tweak the design to do so. But the rest of that space will be full of SK Low antennas in about 18 months. And very pleasingly, we have this small but vitally important milestone, which is the first 24-hour all-sky image from an SKA low station. Worked first time out of the box. Little secret to everybody, hasn't worked since. Something in the software changed, but the team are working on it. But I was so pleased to see that, that all-sky image. Just a demonstration that the system is there. Key challenges. Every project is hit by this: inflation, labor shortages, supply chains. We're working with our members to solve that. Spectrum management. It's been a big theme of this General Assembly. This is a 2-hour exposure from a national park north of the SK Low site. Nearly everything you see in there is Starlink. And to us, each one of those is a moving radio source. So I think you're all aware of how hard we and colleagues are working to protect the dark and quiet skies. My construction manager in Australia says when we build telescopes, droughts break. And yeah, you can see the effect. That truck isn't moving for a while. It's actually cleared up now. The weather has improved. But we actually were down to 4 days of food at the camp, and we had to use the DG's helicopter to go in and deliver extra food. It's a joke. I don't have a helicopter. We rented a helicopter. That's another challenge. It's unpleasant working conditions out there in the height of the summer. So we're very careful with our health and safety. I don't know why the headlights are on in that car. Anyway, so the level of risk the project has increased because of that global situation, but we're managing it. I hope I've just demonstrated that construction activities are proceeding. We had our first light as planned last month, and it's been a 35-year journey, but science is now on the horizon for the SKA. And I think we're engaged in one of the great scientific endeavors of the 21st century. So thank you.
Thank you, Phil. Let's just take a couple of questions of fact or clarification, and we'll leave the more complicated questions till Carl.
Thank you. So I was wondering about are there any technical differences between the Meerkat dishes and receivers and the SKA ones?
There are. First of all, the Meerkat dishes are 13.5 meter, the SK mid a 15 meter. So that's a difference that radio astronomers are used to being able to manage with different dish diameters. The receiver systems are incompatible. They're not incompatible, but they require a significant upgrade between Meerkat and SK mid, mainly in terms of the digitizers, the back ends. So that's a change that has to be made as we incorporate Meerkat into SKA mid. But that we know exactly what we need to do there. It's all planned. So that will happen at the appropriate point.
So you mean the Meerkat dishes will get SKA receivers?
They will keep the current receivers, and parts of the back ends of those receivers will be modified.
I see.
Okay, perhaps we should, one more quick question then.
Jenny Driggers, LIGO Laboratory. With the phased installation plan, how does that affect your observation capabilities? Are you able to observe and install at the same time, or does that mean you have to come offline for a while? That's maybe an ignorant question.
No. We hope to have a continually evolving system, but your question is very relevant, because even now, as we are constructing in the middle of Meerkat, we are causing interferences to the Meerkat science operations. So what we're attempting to do, we have fixed working hours during the day, and at night Meerkat is able to do its observing. And undoubtedly, until the whole thing is completed, we're going to have to keep a regime like that operational. I mean, it's just a fact of life. We're building in the middle of an operational system. But as we get further out along the spiral arms, that should become a bit easier.
Okay, let's thank Phil again. So the last talk of this session is Tony Beasley to tell us, he's the director of NRAO, to tell us about the NGVLA project.
Okay, thank you to the organisers for allowing me to talk about NGVLA today. What I'm actually going to do is introduce you all to NGVLA, and then in a session on global coordination and planning, talk about some adjacent topics as well. As we speak, NRAO is operating two of the world's great instruments. There's the ALMA array that we operate with our European and Japanese partners in Chile, and the Jansky Very Large Array. Now, the VLA is 44 years old. It is still the world's premier telescope, although times may be changing. The bottom line is that, the VLA has been an incredible workhorse for the astronomy community, all frequencies, all wavelengths, over many decades now. That said, it is time to think about what the future holds. What are the science opportunities? And in particular, the concept that we have been exploring based on interactions with the US and global community is the next generation Very Large Array. So the goal of NGVLA is to produce an integrated instrument which has 10 times the sensitivity of the current arrays, 10 times higher resolution than the VLA, works over an expanded frequency range, 1 to 116 gigahertz. And the way to do that is to build more antennas. And so NGVLA is 244 18-meter antennas and 19 smaller antennas in the core. Now, this is a replacement of the VLA. This is actually based at the VLA site. Of that 244 antennas, I think 190 of them are still at the VLA site, with the rest of them sort of deployed around the desert Southwest and out to the VLBA, and I'll show you that in a moment. So the technical baseline, I talked about the frequency range spanning H1 up to CO, the main array of 244 dishes, core spiral mid, I'll show you in a moment. There is a short baseline array. This is smaller antennas, which enables you to have improved surface brightness sensitivity on the sky. Over here, you see the different bands that cover the frequency ranges, and then some information about kind of data acquisition. Typically, for those frequencies that allow it, we're pulling 20 gigahertz of bandwidth back dual pole. So this is the 18-meter diameter antenna. It's an interesting antenna in our community in the sense that we've built smaller antennas which are more precise, and we've built larger antennas which are less precise, and this was just sort of interestingly in the middle. We wanted a larger antenna with very good precision up to 116 gigahertz. So this has been designed by our German colleagues, and right now we are building, well, in an hour or two, we are building this prototype at the VLA site. It's kind of a cool picture, the past in the background and the future in the foreground. So this one antenna has been funded by the National Science Foundation, and if you're going to build something that has 244 of them, you need to build one of them and show that it works, and that's what we have underway. So this antenna will be observing by early next year. We have antenna variants. I mentioned that there's the small diameter antennas on the left here. You see the 6-meter design produced by our Canadian partners. Is this the design we're going to build? That's unclear. This is a reference design. On the right, however, you see a particular variant of our design that goes to lower elevations. Part of one of our partners at NRAO is the US Naval Observatory. They have particular applications that require lower elevation observations, and so we've produced a design variant, and I think we'll actually be building a prototype of that within the next year as well. In terms of front ends and data acquisition, I mean, there's a lot of SKA and we, NRAO in general, there's a lot of knowledge and experience in this. We have 6 data acquisition receivers there, 6 cartridges as we call them, 2 cryostats. An interesting part of the design here is that these are about as good as you can do thermally, but they really need excellent mean times between failure. And so part of the design that is going in here and the prototyping is to produce very robust systems that don't need to be touched constantly. This is the configuration. If I start here, this is kind of the core of the array. You then see on kind of scales of the current VLA a 5-arm spiral. That 5-arm spiral continues out into sort of the desert southwest, northern Mexico, Texas, Arizona, and so on. And then on the larger scales, you see you kind of essentially link up with the VLBA. So this is a big part of the NGVLA concept, is to actually combine the VLA and the VLBA into a single instrument, common hardware, be able to observe on all angular scales. And you see over here, these are the long baseline antennas. And where this is actually Rev-E, which is not the baseline Reverend. Just in general, we continue to explore where we're going to put these antennas, particularly on the long baselines. We can revisit some of the decisions the VLBA made years ago. So the key science goals, a lot of it is very similar to some of the SKA stuff. Movies of planets, I'll show you in a moment. We can map the protoplanetary disks within a few hundred parsecs. Origins of life, using NGVLA, we can actually look at the complex organic molecules in lots of those objects. Origins of galaxies, looking at cold molecular gas in the nearby universe. We can, if they can be detected, if they exist, we can look at millisecond pulsars near the galactic center and test GR. And then there's just the full spectrum of black hole physics. I mean, we still make a lot of images of jets on all different scales. We still don't exactly know how that works. With NGVLA, there are hundreds or thousands of more objects for us to look at to try and understand. And this is kind of the single shot. This is kind of the killer application, we used to say. This is an image that can be made from monthly observations of NGVLA of a protoplanetary disk within a few hundred parsecs of our system. And there are 400 or 500 of these systems accessible to NGVLA in future. So that's very exciting. You can look at the chemistry of those objects and come to some conclusions about the formation of planet and perhaps life. So there's been discussion, Pat discussed earlier, there was a decadal survey once upon a time, and emerging out of that, there were, in particular here, there are opportunities for the US system, US ELT, CMBS4 and NGVLA. As it has turned out, life was not as simple as we were imagining back in 2019, and all of these projects are kind of moving through the system at some level. The goals here, you can kind of see when these different instruments are supposed to be online. NGVLA is roughly 10 years from now, so we better get on funding it. That is not a long time, 10 years to build an instrument like this. Just sort of broadening the discussion slightly, if you look at sort of sensitivity and frequency here, you can look at our community, and this is where we sort of start to, I get on my soapbox here. If you start to think about what capabilities are the global radio astronomy community providing, this is a diagram that shows the detailed sensitivities of these different telescopes, but in reality there is a coordinated effort here, in the sense that SKA is will be truly remarkable at lower frequencies. NGVLA will cover the centimeter to millimeter, and then ALMA is outstanding at higher frequencies. And so, these instruments are overlapped in frequency range, they're overlapped in capabilities at some level. There is a sense of coordination here. We're all aware of what the science opportunities are and what we need to do with our instruments to bring this forward for the community. And I do think that coordination exists in the radio. We are very familiar with our developments. So strategically, we have kind of the right plans. And the difficulty, as we've heard today, is time and money and the things that plague projects. Pivoting slightly, ALMA. So ALMA has been an incredible success. We're in cycle 11. Essentially, ALMA is considering a future upgrade, and if we assume the 25 years rule, that it's 25 years from inspiration to full science operation, it's time to get started, right? We do not want to be bringing on a major ALMA upgrade in 2050. So we want to before then. So the bottom line is that there are key science desires, built on what we have done with ALMA. We can understand where the interesting science lies. So the kinds of things that can be thought about are things like 10 times the spectral sensitivity, longer baselines for ALMA, that's a hard one, wide field of view. ALMA is a fairly narrow field of view. And so as we have these discussions, there are different science community and national instruments interests visible. And so I think it's an important moment now for us to start thinking about what this would look like, bringing the right people together to start to consider what the next version of ALMA would be. Now, it is a difficult time. The current ALMA partners are busy. We've seen some of that today. And of course, aligning the funding here can be quite complex. In the US, for example, there's the decadal survey. And so even with a fair wind behind us now, we're going to have to run probably 2 surveys at this point to get to ALMA funding for a major upgrade. So that's 15 years. So I think that in general, in a system which is struggling to deal with the last decadal survey, we probably need to be a little more strategic about what we do going into the next decadal survey, because it is the case that the scale, both fiscally and in terms of time, of our current ambitions and our future ambitions, they really require a significant evolution of the US system, the ground-based system. In a decadal survey process where the average time to actually build one of these telescopes is a decade and a half, there's a mismatch, and it is getting worse. Yep. And just in general, AUI and NREO, we are working with the ALMA partners, and we do kind of hope to make some progress in this. This is an odd topic. I got asked this question yesterday. So there's been some amazing US and China collaboration in radio astronomy in recent years. We've built instruments for our Chinese colleagues. We've worked on joint projects. We've followed up on amazing fast observations and so on. And that has taken place despite the fact there's a lot of non-science stress, if you know what I mean. So what we do here is that there are several major facilities that have recently opened or under construction or consideration in China, and that's at all wavelengths. I mean, in space and on the ground and in the radio and so on. So at the agency level, at least in the US, a lot of that interaction is framed as a competition or a threat. And I think we would all understand it would probably be more useful for the science community for that to be a collaboration, a scientific collaboration. So I'm a big fan of science diplomacy, showing that we can work together successfully in some areas. And so I kind of wonder in this group and just in general at an IAU, should we be working more towards that and thinking about it as an explicit goal? And if you've sort of ever heard about disruptive technologies coming along and taking over, it strikes me that this is what we are facing now. That if I look in particular at millimeter and centimeter astronomy, SKA is coming along, amazing SKA, and China is building a lot of instruments. And just in general, while the US has enjoyed its share of world leadership of radio astronomy over the years, the centroid is moving. I don't know if it's moving east or west, but it's moving. And so we need to be aware of that and thinking about the kinds of partnerships, both with SKA and with some of these other projects in China that would produce better science, not just better institutes. So in summary, the NGVLA project, with its science case and technical plan, has a lot of support, and we can capitalize on other investments and really make a major step forward in radio astronomy. The project is underway, and we've got lots of major milestones in the next 12 months. A construction decision is 4 or 5 years away, I would say. And there are a lot of synergies, as I pointed out, with SKA and ALMA. There is a major ALMA upgrade ahead somewhere. We need to get started in a sort of international way. Our Western-centric approach to strategic planning may need some revision. I offer that for suggestion. In general, the centimeter and millimeter, one question I'd toss out there is, are we seeing the last generation of ground-based instruments without major technological advances or compelling non-astronomy use cases? I mean, Phil will remember the start of the SKA was an assumption that we'd be able to produce collecting area at 1/10 of what we were doing then. And in fact, we haven't got any cheaper in the remaining 25 years. So, if we really need instruments that need 100 times the current collecting area, it's probably not going to happen. So just interesting to think about that we can't ignore the technological developments that might be required to get to even the next generation. And just in general, NREO, NSF, and the US radio community are proud to support all global planning efforts. Thank you.
Thank you, Tony. In an attempt to see if there's really people online, you and Phil both pointed out that there's a lot of activity in China in this area. I just wondered if there's anybody in the room or online who can comment from the point of view of the Chinese community, how these things are perceived there. Is there anybody online that might be able to do that, or anybody in the room?
Well, that's a data point.
Okay. Okay, specific questions for Tony. Dave.
Hey, I'll start with this snarky remark of I don't necessarily sure that the NSF would be in that last group right
That's
now.
snarky, yes. I
But
confirm
thank
that
you.
is snarky.
Yeah. This is actually a question. Oh, I don't know, who should I say? I am an anonymous astronomer from the university. I'm David Silva from the University of Texas, San Antonio. This is maybe a question for everybody. It seems that you mentioned the upgrade, and it seems to me that although it's not necessarily a challenge today, it's going to be 10 years out because we're now building these major new facilities where upgrades, quote unquote, are going to cost the same both in terms of sweat equity and capital as facilities did 10 or 20 years ago. And, you know, to your point about in one of your slides where you talked about, you know, at least in the US, things are stressed in this regard, and I think they are in Europe as well. Gosh, it's going to be really, really hard. We're good. We're making progress and putting in these new major facilities and getting capitalized and operated. But it's going to be really hard to build the next generation of the upgrade or the instruments, given the cost profiles and the somewhat shaky political grounds we're on right now. I was interested if you must be thinking about this because of ALMA. So that's really a question for Bruno and Pat and Phil as well. So the question is, how do we deal with this as a community? Not only should we be coordinating on building like something that big that's new, but how do we actually coordinate doing the upgrades in the next 10 or 20 years?
Do you want to have a go at that, Tony?
I'll let Bruno start.
That was a good one. So ALMA is going through an upgrade right now, the wide field sensitivity upgrade. And so that's happening with us in the partnership. We're talking. You know, the idea is what's going to happen later and how do we set that up. I will probably say something a little later in the ALMA session about what ESA is thinking about.
I was about to make that comment that there is quite a lot of consideration in the report from the Kavli workshop, which happened in March, about what will happen to ALMA after the wide field upgrade. So maybe we should pause that discussion till then. Specific questions for Tony. Let's start with Lynn and move along.
So this morning, sorry, I'm Lynn Hillenbrand from Caltech. This morning we heard from our space colleagues about these categories of small, medium, and large missions. And I think in the optical realm, there's also discussion of very large, medium size, and then smaller telescopes in the ecosystem. In this, I didn't hear, I heard only about large projects in this session. And so I'm wondering, what is the role of university, either large universities or small countries? What should they be doing technically to either do independent science or to advance the large projects?
Yeah, I can have a go at that regarding radio. I mean, there is a pretty healthy population of university scale, mid-scale instruments that have been considered for funding by the NSF. As it turned out, one of them was. Advanced Simons moved forward, the others perhaps not so. I think it's a good model, and it's actually the model upon which ALMA was founded. There was the University Radio Observatories, and emerging out of that were all the people that built ALMA. So it is certainly a viable thing. It's just difficult in a system, particularly the US system at the moment, where operations funding is so hard. So if a university makes the investment to build one of these mid-scale facilities, $100 million or something like that, typically they're looking for NSF to come in at the operations level, and that might be 5 or 10 million a year. And that really just seems to be an amazing stress point for the NSF right now, is being able to find $5 or $10 million a year to operate one of these facilities that it's being handed, basically. So I think there is absolutely a place. I grew up through that system. There is absolutely a place for that. But what we have seen recently is that those mid-scale projects are not all being funded, and there's really not a lot of mature discussion about the operations of them. So it's tough. It's a tough moment.
James Lowenthal again, Smith College. This is the radio corollary to my earlier question about light pollution. Can both of you speak about the vulnerabilities of these radio facilities to the prospect of 500,000 or 1 million Starlink-like satellites or bigger and brighter with direct-to-cell coming? Looking at your picture of the spiral stretching across multiple states in the U.S. and down into Mexico makes me think a radio quiet zone is an impossibility. What are your thoughts about what our community can do to protect these assets?
Sure, I went, this Phil. I gave a short talk on this earlier in the week or last week. In the radio, the situation is a little different to the optical in the sense that in particular the interferometers have a certain robustness against this, natural fringe rate being what it is. And so we have done a lot of tests with Starlink, for example, on their internet service about the impacts. And there are impacts, you can detect them, that's for sure. But we've come up with mitigations that I think at some level have largely addressed some of those concerns. Now, the direct-to-cell thing is a real problem. And I think, it's a moment for pragmatic reasoning. The reality is, as a safety service, probably the US government is going to push this through. So what we need to do is try and shape that so that one of the mobile bands is used. And in general, Phil is in very radio quiet areas, and so he's not necessarily dealing with the same issues. But the problem that we're facing now is instead of the mobile cell signals coming at you, scattered through the horizon, they're coming from directly above you. And it is impactful. So we just need to continue working that problem. There's no great solution to it. I don't really believe there's going to be 1 million satellites in the sky. I don't think there's enough money in the world to do that. But the problem could be 10 times worse than it is now. At the moment, at least, we do a lot of work in this area. We're not seeing catastrophic issues. It could get worse.
I'm the next. I'm the next one.
Yeah, you're next, but give your name.
Okay. I'm Chen Zhou from National Astronomical Observatory of China. So I'm very excited to know the exciting progresses for the extreme large telescopes in both optical and radio wavelengths. So you just mentioned about the China problem. So I just say several words on behalf of myself. Yeah. So the Chinese astronomy community is very open and very keen to be involved into the global astronomical community. And so, however, it is a pity for the whole world becomes complex now. So everyone is unhappy that. For the astronomy projects, for example, in the early of this year, the Chinese community contributed Einstein probe and GCAM satellite missions fit to the GCN network, and the fast radio telescope opened the time to the whole community. Of course, for the other optical projects, the Chinese astronomers are very open. It's disappointed for the whole world situation becomes complex, but it is out of the scope of our powers, our discussion. So we sincerely hope the world is open and the sky is for all of us. Yeah, thank you.
Very good. I think Phil and I were very honored to be at the opening of FAST. And I remember standing there on the edge of it and looking out, and it's 440 VLA dishes equivalent. And so there's more collecting area in FAST than there is in all of NGVLA and SKA put together. And I believe that China is about to build 5 more of them. So there's an old saying that quantity has a quality all of its own. It's interesting to think about, wow, you all will drive the direction of some areas of radio astronomy. And that's what I think we should collaborate on.
That sounds like a really helpful note to wrap up. Thank you very much for your remarks. Thank you. Okay, so we regather in 30 minutes when we'll move on to far infrared millimeter topics.
Yeah, I did the same, but I saw only one. Na oyo programme oyo mutu oyo ya introduction oyo aopresente mpe Gabi.
Restart. And I want to say a couple of things before we actually start the formal session. So if you could take your seats, that'd be good. And maybe as we come in, we could close these doors because there is a bit of background noise. The 4 sessions that the working group has organized kind of fall into 2 halves. We finished the sort of review of the big projects half, and now we're looking actually at 2 sessions, this one and the one that's tomorrow morning, that certainly owe their roots to the Kavli workshops that have occurred. So just for those of you who are perhaps not aware of this, the working group has had the responsibility and pleasure of organizing a Kavli workshop between the last few General Assemblies. So the first one was on the Louvois telescope as it was then, and I think you can sort of trace the evolution of that into HWO. The second one was here in Cape Town in February 2020 on transient follow-up. And the third one was in March of this year, organized by Evine and George Helou on the topic of this session, future far infrared and millimeter facilities. I have to say, I'm very grateful to Evine for organizing that and for producing an extremely good draft report. So I want to thank her for that, but I also want to thank her for something else, because unless I'm mistaken, this is her penultimate day as the past president, responsibility which she is relieved of on Thursday. So as well as introducing her as the introductory and overview speaker, I'd like us to thank her for all her contributions to the IAU. The floor is yours, Evine.
All right, good afternoon, everybody. It has been my pleasure to be a part of this particular working group because global coordination and large facilities have been very close to my heart. I was wondering whether we could get the slides up. I know they're still uploading some talks that got lost somewhere in the middle of the ether, but yes, here we are. Okay, so we've gone from space missions, we've gone to large ground-based optical and radio telescopes. Now we're going to go to far infrared, millimeter and centimeter astronomy, which was the focus of a workshop that we had in Pasadena in March this year. And so for those of you who were not here in the earlier sessions, just a big reminder that, of course, we are very, very fortunate to be doing astronomy at this time with all these fantastic facilities that we have both on the ground and in space. And together they address the main science themes that we've also been hearing about, galaxies, formation and evolution, from the very highest redshift that we've seen with JDBST to the presence this morning with H1 from Meerkat. Formation and evolution of stars and planets, fantastic talks, especially about exoplanets, the Kavli talk that we had from Dave Charbonneau. Lots of things happening there. And then the new messengers, the new physics that we're having, and we'll be hearing more about that, well, last week already in the gravitational waves and more tomorrow morning in the fourth session of this working group. So to address these questions, we all know we don't need a single facility, but we usually need a combination of facilities across all the wavelengths, and now also multi-messenger. And this is just a small overview of the many very powerful facilities that we actually have. Now, the IAU has been concerned with global facilities for quite some time. This is actually a page from our strategic plan, 2020-2030. Just to illustrate that we have many plans and many dreams all the way up to 2050. But these facilities have become so large that no single nation or even a single continent these days can afford the biggest ones, and so we need collaboration there. What you also see already in this particular figure is that there's a quite substantial hole actually there in the far infrared part, especially from space. Okay, so what is the role of the IAU actually in all of this? So what the IAU actually forms a neutral forum to bring various parties together. And we do this from across the entire world. So this is a bit what Tony was referring to. We shouldn't just have our Western based view of this, but we try to get together really people from across the entire world. And that's also what we did in Pasadena. We had from 6 continents. These kinds of discussions are most effective at a very, very early stage. We are sort of planting the seeds for the future. So we're really looking far ahead by at least 20, 30 years. That's at least what we are trying to do. So we have this working group on global coordination. Its importance is in the fact that it reports directly to the executive committee of the IAU. In contrast to many other working groups and commissions. We have a 2-day meeting every GA. That's what we're having here at this very moment. And then we have one focused workshop in between the GAs on a focused topic. And the Kavli Foundation has been very kind to support us for these workshops. So big thanks to Greg Mack, who is here, and the Kavli Foundation for doing that. So we've had indeed 2017, 2020, that should have been 2020, transient astronomy, and then 2024, that is when we had centimeter, millimeter, far infrared. And of course, these are complemented by lots of other workshops and meetings, sometimes agency organized and therefore also more region organized, but also other facilities, especially ISI is very active actually in the planning of space-based facilities. So a very important point is we produce reports, but we do not prioritize any facilities over others. We basically try to give the arguments for moving forward in the various cases. So why this 2024 workshop? Well, it was actually very timely because of various recent strategic plans. Of course, the Astro 2020, which led to habitable worlds, but also to the NASA ProPrime, which has the far infrared as one of the options there. Also CMB4 and GVLA study are in there, so these all link to what we were discussing in Pasadena. Another example is Voyage 2050 from ESA, which had as one of the themes also infrared astrometry, but also infrared interferometry. So that linked also in some way to our discussions. And of course, there are many more plans across the world. We heard from some of them, for example, from China. We've heard earlier already from Japan about what is happening in their countries. And this is complemented what we have in the space, of course, by what we have on the ground. And ALMA is operational, but as we will see, there's more work needed there for the longer term future. We have the ELTs, beautiful talks earlier today. LSST is coming, and we have also the interferometers also on the ground. So that is sort of a landscape in which we are operating and need to formulate the science cases for this particular wavelength range. So we're starting centimeter at about 20 gigahertz, so we're not talking about the low frequency part. And then we go up to sort of where JDBSD ends, which is around 30 microns. And this is, of course, the main science theme is here, the cold and dusty universe, the formation of galaxies, stars, and planets. So the major reason for having this discussion now is the big NGVLA endorsement. We've heard about that earlier from Tony Beasley, design study, followed by reviews, then to determine the project's readiness. ALMA's future, there's going to be the wideband upgrade that is happening at this very moment. That will be ready by 2030, but then really the question is what comes after that? What kind of ALMA do we need by 2040? And then also the question, who takes care of ALMA at that stage? Because all of the partners are, for good reasons, busy with either ELTs or NGVLA. And then far infrared in space, we had Spica's cancellation, unfortunate, in 2020. And so there's now this new opportunity through the NASA probe lines. So just a few slides on each of these. Here is the far infrared, just to show you that this is a really wavelength regime where still with relatively modest investments, huge gains in sensitivities are possible. This is sort of the sensitivity gain compared with Herschel PAX, which was the previous facility in this wavelength range. And you see that whatever of the three concepts you use, you typically have a gain of about 5 orders of magnitude. There are indeed 3 concepts that you see here. First, prima, saltus. They differ in their strategy, surveys versus more pointed. Saltus is an inflatable dish of about 14 meters. The others are more 2-meter class cooled telescopes. So that is also one of the differences between spectral resolution is another difference, precise wavelength coverage and technology. NGVLA, of course, the next big jump at centimeters wavelengths. So here is just the comparison with ALMA. So as Tony was saying earlier, the aim is really to basically have a factor of 10 increase in the collecting area. That, of course, gets you much more sensitivity. And then by spreading it around the United States and Mexico, then you get also an increase in spatial resolution. So that allows you to really zoom in into regions where you still otherwise would lose the sensitivity in order to image that. So that's a huge way forward there. There's also the large single dish that was discussed actually in Pasadena. So this is actually driven by the enormous increase in technological developments of array receivers, going from sort of the JCMT Scuba type facilities to what we will hear about a little bit, LMT, Toltec, and then the dream then to go up to 10 to the 6 pixels. And so there are several studies that were actually reported in Pasadena. And then coming back to ALMA, what is ALMA's long-term future? It's very highly oversubscribed, very popular transformational science. The wideband upgrade is happening, but that only gives a rather modest increase in sensitivity. As we will see, there are many fundamental questions that actually require individual line sensitivity rather than observing many lines at once, which is enabled actually by the wideband upgrade. So that is something to discuss, and it's actually a major point, and I'm very glad to see that NREO is sort of taking the lead on this in thinking about that future, because that is one of the main outcomes actually of this workshop. So recall that by 2040, JWST will have had 18 years of observations. It may be ended already. ALMA has had 27 years of observations, the WSU maybe 10 years, ELT has had about 10 years, SCA1 has had 10 years. So, you know, you really need to try to force people to think about what is the scientific landscape by 2040. So we had about 50 people by invitation in Pasadena, mostly organized by George Hilou and Jonas Smoutsinas. Very lively discussions. As I said, people came from all around the world. Broad consensus on the science directions, and it was a very good way of meeting new people and mingling. So we particularly targeted sort of the mid-career people to come here to this workshop and interact. And here you see a photo of it. We are now at the stage that we actually do have a draft report that is actually circulated among the participants for comments, and we expect those by about next week. Here you see actually the SOC. The SOC basically was responsible for the workshop report. Alberto Ballato is here in the in the meeting room. He played a large role in it, and you see several other people here as well. So we expect the final report to be ready by mid-September. The executive committee of the IAU, of course, also has to endorse it, and then it will be on the IAU website and on archive. And here is really the big thanks to George Hilou, who really pulled off the major part of the writing in this particular report. So this is the outline. As you see, we're going through findings, and then we also go through recommendations on each of these facilities. And let me just go straight to the recommendations then. The first one is to basically put these ideas for ALMA by 2040, a major upgrade of ALMA into high gear. It's really getting urgent now. If we want to have another ALMA an improved ALMA by 2040, we have to start now. Interestingly, it was quite very considerable consensus that it should be the collecting area that should be improved, only modest increases in the baselines. That was not the major driver, it was really the line sensitivity that was needed. NGVLA is a great facility to look forward to. We had very good discussions on that, and we really encourage also to develop further international partnerships. The far infrared probe is urgently needed. We have had this we are losing expertise in the community on both on the science and the technology. Any of the 3 probe concepts would be fantastic. So that's our recommendation to NASA here, especially because of the orders of magnitude improvement discovery space. We, as always, urge them to sharpen the science gate still further. The large single dish, wide field service, they really complement the other facilities. We felt that still some further studies on the science and the technical aspects and also the involved costs were needed. CMB4, please go ahead, because a lot of that data, in addition to cosmic microwave background, can also be leveraged for other science. That was discussed at this workshop. And we also encourage to involve a wider community beyond the long wavelengths, especially in this large single dish. Data analysis and archiving need to perhaps be even more an integral part of the observatories than it is now. Certainly not cheap. We know that. ALMA, of course, has done already very well in that, but we hope that that will continue, obviously, also for the future ones. Continued technology development is essential. As Tony also said, a lot of the current technological development came from the smaller facilities where universities were involved and driving some of the new technology. Maybe be stuck, as Tony said, because we haven't invested enough in new technology development. That's obviously a very important point. The time allocation process, there was some worry expressed on balancing large and longer programs versus smaller programs, especially also to populate the archives. Now, some of the archives now are very inhomogeneously populated, and that makes it much more difficult. That prevents basically doing archival science. Enable, of course, also time domain astrophysics. We'll have a talk on that. And then the facilitate the high frequency polarization ALMA that is still rather difficult in the current system. Other recommendations: preserve this expertise in the community. We need young people to analyze the wells of data. Certainly the line surveys are going to be so rich that we need a lot of good, bright minds there to do that. As also in development of the analysis tools, in providing also the databases. Sometimes we're just limited by the databases that we have for our gas phase lines, for ISIS, for pH spectroscopy, etc. And then especially the bottom line, get the developing countries more engaged in our programs from the very start. Now, how can this workshop help? Of course, we try to develop a vision of how these fields will evolve in the longer term, 2040. You'll hear some talks about that. We want to stress these synergies and complementarities between facilities. But also this workshop, because always there are more dreams than there are funding available. So what we try to do is this workshop provide some scientific ammunition for cost-benefit arguments that will undoubtedly come up at some stage. Also in competition, not just between these facilities, but also in competition with other wavelength facilities. So some prioritization will always be needed at some stage. How can the IAU help? Well, we bring people together. That's our mandate. That's what we do. Through workshops, through symposia, through the GA, and through these kinds of meetings. We train young scientists actually across the world. I'm very pleased that we have actually Itziar here at Exaga. She's doing a wonderful job with the International School for Young Astronomers. We're at master level and early PhD level. We're training people also in some of the techniques. And now we also have the hands-on workshops led by Mariano Mendes that is really focused on training people in the use of data and archives for world-class facilities, about 2 per year. Okay, so that's it. I'll end here. If you have any comments or questions on what we're doing, please let us know by next week. By that time, we'll be finalizing also our workshop report. Thank you very much.
Okay, so let's take a couple of brief questions on, matters of fact and so on. Any questions for Evine? We're going to have an extended discussion time, but particular points. Yep, David. Oh.
Evine, one of the questions you guys apparently asked, because you had it on your slides, is, what is the impact of AI on this particular subject area? And I'd be interested at least in hearing how that discussion went.
Well, it's a good point, because we flagged it as it's something, but we realized we really didn't have the competent people at our workshop to answer that. So that is why I flagged it here, that it's something we need to, probably all of us need to think more about, also in the previous sessions. Yeah, please go ahead if you...
Well, I think there's some synergy with what you said about the archives being uneven and messy, because at least, one of the directions we're all aware about is these large language models and ChatGPT and things like that. And those are really becoming the frontier for kind of information organization. And so I think a lot of people focus on things like, how do I find structure and groups and things like that. But it may be that one way we deal with our global issue, the kind of thing that the VO tried to do 20 years ago, there may actually be ways forward with some of our colleagues in the knowledge organization area. So I would encourage us to think about that.
Yeah, absolutely.
Okay, this will be the last one, and then we'll go on to the science talks. Can you say who you are, please?
I'm Paul Barrett from George Washington University. Talking about software. Software in astronomy has always been broken, or basically has never worked properly. I think we need a new model for it to actually make it work properly. I just wonder if you have any thoughts on that. I know I do, but.
Well, I mean, I'm a very pragmatic person myself. I just like some system that works. It doesn't have to be the optimal system. And for me, it's actually the simpler, the better. Some systems are actually becoming too sophisticated, that you don't have any control anymore of what you're doing. So I'm personally more in favor of keeping things simple and make sure that you can use them easily and straightforward.
Yeah, that's a topic of several workshops in itself, I think. Okay, so we're now going to try something extremely dangerous. We have 5 science talks. Each science talk is 8 minutes with 2 minutes of questions. Itzia, would you like to come to the front while I'm talking? Because this is an example of how I want to run this. We've just watched the Olympics. This is going to be a relay, right? So they will pass the baton one to another. And I'm going to have to be very careful about the timing, because, 5 talks can overrun very quickly. I think, oh, the clock, it's fallen over. Yeah, there is a clock here. There is a clock. Sorry, I hadn't noticed that. Yeah. Okay, so I'm going to give each speaker 6 minutes. I'll give a 2-minute warning at 6 minutes, and then we'll have 2 minutes of questions, and then you get off the stage, and the next person comes on straight away. Yeah, 6 minutes, and then a 2-minute warning, then 2 minutes of questions after that, and the next person comes up. Okay, everybody clear?
Thank you.
The first speaker is Itzia Archaga, who's going to tell us about high redshift galaxies. Itzia.
Thank you. Evine gave a great introduction of what we talk about. We basically consider future missions or future existing telescopes into the 40s onwards. So for single dishes, we consider these projects. For the satellite, the 3 infrared probes that have been proposed, and for interferometers, ALMA NGBLA, and I have taken the permission of using already existing telescopes so that nobody gets angry with me for not putting the project on the first slide. So I will say there was widespread enthusiasm for every single one of these telescopes. And just a reminder that we are going to just be considering the millimeter to centimeter wavelength, where we are sensitive to the emission from dust and the plethora of molecular lines that come in these galaxies. This is a galaxy for redshift 0. Eva will talk about that in great detail, but now imagine this and spectral energy distribution just being shifted to higher redshifts and the science we will be able to do with it. So the general recommendations was that the optical surveys are going to be really, really powerful, but a complementary view of the universe in the obscure universe was not there. And it was not going to be supplied sufficiently with existing facilities, and therefore our enthusiasm for the proposed missions. So clearly, the Far Infrared Space Probe is clearly supported by the community. It will trace the peak emission of luminous baryonic matter and its mass, and it has orders of magnitude increase in sensitivity related to previous missions. Single disc sub-millimeter to millimeter signs, yes. We have the LMT, it is working. We have a powerful camera that still has to be delivering the signs, but we hope it will be certainly before 2040. And a 50-meter single disc telescope with large field of view, fast service tool is a necessity. And the necessity is actually just shown in this diagram. What we are seeing, the star formation contribution to the universe at different redshifts, the optical view without any dust corrections, and the infrared view directly from our telescopes. And please realize that the upper limit for the contribution of the infrared comes in this line here. So there is a huge uncertainty to how we measure star formation rate in the universe nowadays, due to the very small fields we can trace. And finally, we consider the impact of having a more sensitive ALMA and the NGVLA into the high redshift universe. Okay, so this is where we are now. Evin said, so Herschel is not enough. No, Herschel is not enough because it doesn't go to high redshifts. We have hundreds of thousands of sources from Herschel. They are heavily confused. We cannot actually efficiently tie them to the optical counterparts, and therefore it is no match for the future optical telescopes. This is where we are now with ALMA. Tiny fields, 20, 30, 50, maybe 100 at most sources, spread over all redshifts, and therefore not knowing what the real contribution is. Or targeted surveys that give us a completely different view. Targeted surveys tell us there is a lot of dust at high redshift. Blank field surveys up to now in tiny fields tell us there is actually little, and the question is not resolved until we have a good surveying machine. So in part, that will be realized at 1 millimeter wavelength, but certainly it will be complementary with a large 2-millimeter telescope. So this is the simulation work we have been doing in my institution at INAOE. Just to give an example, this is 20 sources with ALMA in 14 hours, yet cycle 3, so only 40 antennas. And these are the sources in good south. This is what we think we will be able to do with Toltec, 1.1 millimeter simulation, 60 hours, half a square degree, 25,000 sources. It has to be realized, of course. This is a simulation. So apart from the surveys that will actually uncover what the star formation rate is directly by measuring the dust contribution, we will also like to do line emitting surveys. Basically, there was a big endorsement for this new technique, which is the line intensity mapping. That doesn't really target galaxy by galaxy. This is just the review paper in Annual Review, where this technique is explained. This is a simulation of all the galaxies that you will see in a 1 square degree. This is what you are sensitive to real with telescopes. But if you actually integrate the line emission without worrying what galaxy it comes from, then you have this type of detections. And this is a very powerful thing because statistically you can actually invert your line mapping and recover statistical properties for the population, such as the luminosity function, and also map the large scale structure in the universe at different redshifts. So this is the tomography of the universe in just one slide. Very, very powerful. So this is exactly the same. So let me just go to the science goals. So the science goals, by just just putting together all these facilities are through the mapping of dust, we will be able to recover the star formation rate by having great accuracy in the positions. We will be actually be able to measure what the galaxy mass buildup and the assembly, especially when we go then to high resolution imaging. The evolution of gas and dust through time will speak to us about the metal enrichment history of the universe. So everything is statistical in a sense, right? And the direct observation of interstellar dust through spectral features and polarization at or near the infrared peak will also be very important. The infrared probe actually speaks about the co-evolution of black holes and star formation. So independently, also very important to actually try to derive what is the history of evolution for galaxy formation. And finally, although this is not galaxies, but it is high redshift, the Sunyaev-Seldovich cluster abundance gives us important probes for cosmology. Single dish infrared probes will be pathfinders, but certainly we need the high resolution in order to measure accurate properties of all these galaxies at high redshift. So this is just an example of one of these high redshift galaxies measured with JWST, and the counterpart of what we can find right now with ALMA. ALMA with new sensitivity and with increased bandwidth clearly will be able to measure the molecular contribution and the dynamics in a much better way, also combined with NGVLA. Thank you.
Time for a couple of questions. Okay, yeah, so Eva, come up for the next talk, which is nearby galaxies. Eva Schindler.
Yeah, thank you everybody for coming here. I was asked to talk about science that can be done with nearby galaxies, and how do I move?
Just a big green button.
The big green button. Okay, so everybody is familiar with the galaxy, how it looks like in the top left. That's the optical image. The one in the bottom is basically how it looks like if you were able to get the ISM at very high resolution. So galaxies can basically be seen as being an ecosystem. The high redshift observations, you expect gas accretes from the intergalactic medium. Somehow within the galaxies, there's a lot of going on. You see galactic structures, which might cause gas flows to happen. Inside the gas flows, you also have star formation. There's a baryon matter cycle that the star formation from cold gas ends up being stars and both dispersed. You do see metal enrichment in these galaxies due to the star formation, and the stellar populations can give you basically access to the star formation history. In the center of the galaxies is a supermassive black hole, which might be accreting, which could then also drive an outflow, or a massive starburst could do that. And this gas could be returned to the halo or even enter the intergalactic medium. So in short, nearby galaxies are ideal laboratories for us to study the physics of all these processes that we would like to understand how they change over time, going back to the earliest galaxies. For this purpose, I'm only focusing on star formation and basically use that as an example for the baryon matter cycle on small scales. So what you see here is a small star forming regions, 200 parsecs across or so, and from the diffuse atomic gas, it kind of condenses, becomes molecular, can then collapse eventually, form stars, star clusters. These, during their formation, exhibit winds, radiation, forming H2 regions, exploding as supernovae, basically destroying the reservoir, ionizing the gas, and the gas has to cool. So in order to observe that, you need to observe across the electromagnetic spectrum, and you need to combine all facilities that are available, as Evine alluded to. So the other thing that you want to do if you want to get the star formation process, you need to resolve your population of star forming sites or even the sites itself. So what you see on the top is basically going from molecular gas to the star formation to the dispersal of a single cloud. This can be achieved for nearby galaxies. In order to basically separate these clouds, you need to achieve resolutions of 50 to 150 parsecs, which is about 1 arc second. If you go out to the distance of a Virgo cluster, if you want to push and resolve these clouds, you need better resolution by about an order of magnitude. And then cloud substructure is basically something that seems mostly to be in reach only in our galaxy. So rather than going through what is done, I picked a number of example questions on what to do. So the first one is, how large is the molecular gas reservoir in a galaxy? And what you have to know is a galaxy like our Milky Way is a lot of metal rich. That means we have a lot of carbon monoxide, which we can use to probe. But if we go to galaxies like Magellanic Clouds or even smaller ones like the SMC and beyond, this basically we are using our tracer molecule. And the carbon plus has been advocated as being one of the best tracers we can have. It has, is the strongest cooling line, and what you see here, we only have about 100 maps like this in the nearby universe. At high redshift, people have been observing C+ for a number of galaxies, so there's a clear mismatch, and the challenge is we don't understand our tracer. And locally, we have the best way to separate all the radiation field from the gas and do the study to get the physics right. Another question is under which physical conditions and then occurs the transition from quiescent to star-forming molecular gas. Galactic studies are using a multitude of molecules. However, if you look in the line here, a lot of them are really, really faint. And doing similar studies in nearby galaxies, this is just an example of NOEMA, it takes about 200 hours. And even with ALMA, this is still a long endeavor and takes like 50 hours a galaxy. WSU will help, however, the traces remain faint in these disks. So how much massive star formation is embedded? JWST is clearly helping us. So on the right, you see in JWST, HST color composite from the massive star formation in the center of a galaxy. And in the right, you see the according mid-infrared emission. However, if you look in the center at the millimeter, you start to see a different regime. And this is also embedded star formation that we are missing and that have been well studied in our galaxy. It's a fast evolution from starless clumps to H2 regions, which we might not be catching even using JWST. How does stellar feedback impact its surroundings? On the top, you just see a sketch that how the radiation and the winds, mechanical and energy, how this impacts it. And this is a fairly good summary of our current understanding, even with simulations. Below, you see observations in blue showing molecular gas versus in gold showing H2 regions, and it's very clear the resemblance should be roughly the same timing-wise, but structurally this is way more complicated. In order to do this right, we really need to combine the multi-phase ISM to do this correctly. Another big question is that we haven't been able to answer, and the simulations struggle a lot, is what shapes the structure of a neutral gas at 5 to 10 parsecs. So what you're seeing here is an image from JWST of a nearby galaxy, about 10 kiloparsec or more across, and you see the distribution in the PAH emission, so that's a polyaromatic hydrocarbonates. And you see a lot of you see the spiral arms, and you see holes in there. And now the question is, what is driving the structure? Is a supernova explosion generating the cavities, or is it the spiral arms rearranging the molecular gas? In order to do that, you need velocity information. And what you see here is a map of ALMA, taking 2 hours with a 12-meter array plus addition. And you see that this probably isn't sensitive enough to basically catch the velocity information where you can tell that something is expanding due to the supernova shell or if it is a spiral arm driving. And the challenge basically is disks are faint in CO, and such observations will be very challenging to do, even with the current ALMA. Okay. Only also to make the point why this is important. This is a set of 18 galaxies ranging in mass from something in the top left, similar to the Large Magellanic Cloud, in the bottom right, about 4 times more massive than the Milky Way, and you see that the organization of the structure is very, very different. And we need to understand how this is going to happen. One question that typically comes up is all about what is the role of magnetic fields and cosmic rays. As observers, we have always been easy to say, we don't know, it's hard to observe. However, what you see here is an image taken with SOFIA, the Shark Plus instrument, showing you the dust polarization observed there. And I think important questions is, do molecular clouds inherit their magnetic field from large scales? What is driving the collapse or preventing the collapse of gas to star formation? But also about understanding the coherent magnetic fields across on larger scales. The challenge here is polarization is only a few percent or even less at the different wavelengths where we can observe it. So it requires a high sensitivity in order to be able to observe it. So coming together, tracking star formation in redshift 0 galaxies. The gray bar shows you basically the regime we are talking about here. This is my assessment. JWST is great. It's giving us fine for red. We basically have no information. The data we gathered is not good enough, and it will not help us to make more progress. The ALMA upgrade will be great for bright, but it will not help for pushing to the next level. NGVLA, it's in light green. If it comes, it will be awesome and help here. And just for a reference, this is how it would look like at high redshift. Okay.
Questions on nearby galaxies? Anybody online? I can't see online. Can you guys in the AV team tell me if there's any question online? Nobody in the room? Okay, thanks, Ava. Let's give her a round of applause again. Now Lynn Hillenbrand is going to tell us about variability.
Great, thank you. I was asked to talk about the time domain aspect of far infrared, submillimeter, millimeter, and given the title of variability. I should say that many of the slides here were presented at the workshop by Doug Johnstone, who spoke on this same topic. So just to put this wavelength range in the context of others, I thought I personally am more of an optical UV near infrared kind of person, but so I gave a talk the other day in, oops, sorry, it was a lot of advancing. I gave a talk in the STARS session in my area, which is young stars and star formation. So we've known these buttons are confusing. The ones in the other room were easy, back and forward. So in the optical, we've known, for well more than a century, and that's what astronomers were doing here, was measuring positions of stars and brightnesses, variable brightnesses of stars, mainly in the optical, or exclusively in the optical. And what's important is the duration of data sets, the cadence of data sets, the precision of data sets. When radio astronomy came around, that was more initially understood to be probing time variable phenomena, and that includes both intrinsic to the source, but also extrinsic along the line of sight. And then more recently, we've had capabilities at these other wavelengths to do time domain science. And so as far as I know, there's not, unless Sophia accidentally looked at the same object twice, I'm not sure there's really been much monitoring in the far infrared. Submillimeter has come along in the past 5 or 7 years. There have been dedicated monitoring campaigns, and also now millimeter. And so just to move along, of course, these wavelengths were probing both thermal and non-thermal physical processes. And what one would want to do with multi-wavelength time variable phenomena is fit spectral energy distributions and also measure changes, if there are variable phenomena, the time delays between different wavelengths. And so just like at other wavelengths, important things would be cadence of monitoring, the duration of the data set, the precision of the derived photometry, the sensitivity, and then if you're talking about what I call, transient events as opposed to what I would call persistent variability, then of course, rapid response, time from trigger to source acquisition and observation and so on also become important. But so these are the relevant observational parameters. And then I just wanted to go through a few examples from different areas of science covering both the galactic and extragalactic. And so in that sense, this talk also connects what we've just heard to the future talks, which will be more about galactic topics. So this has been divided into different time domains, so shorter term phenomena and then longer term phenomena to follow. So here we're talking kind of seconds to days. Excuse my incompetence with the buttons here. So on short time scales, we of course have flaring from stars. In young stars and protoplanetary disks, important is the changes in the young star, particularly in X-ray and optical emission, which will then have consequences for the protostellar disk and chemistry, as we may hear in a few talks. There are also explosive events and the ejecta from those and shocks and jets. There's accretion onto compact objects, so that's inflow as opposed to outflow here. And then getting into the transient phenomena, gravitational wave follow-up, electromagnetic sources to probe merger physics. And so I'll just touch on a few of these examples. This, of course, is the sun, and this is ultraviolet wavelengths. And so we're all familiar with CMEs, coronal mass ejections from the sun. This is also a long wavelength radio phenomena. And what I want to highlight here is work that has been done using ALMA, so long wavelength observations of flaring, where the time scale here is a few minutes. And so there's an observation of a flare event. And enough of these objects have been observed that now the frequency of energy that's emitted, the distribution of energies in these flare events can now be measured for a few different objects. So that's in the stellar physics regime. In young stars, flares have also been seen. So this time scale is now more like half an hour. And so this is long wavelength JCMT observations. I suppose that's short wavelengths for many of you, but millimeter observations. Moving on to a different category of object now at the other end of the range would be black holes and flaring from them, where obviously it's accretion from a companion. And so these are observations over a range of millimeters, sub-millimeter, millimeter, and radio wavelengths. And so the time scale here again is about half an hour to see these changes of factors of a few or factor of 10 or so. So again, it's the multi-wavelength and time series monitoring of these flaring that would capture these frequent flaring events. This is a somewhat older figure, which you can tell by the names of some of the facilities here, but the illustration is basically the long wavelength, importance of long wavelength capability for probing some of these more transient objects, so GRBs, supernovae, tidal disruption events, and so the, again, outflow and impact of that ejecta in the circumstellar and interstellar medium. So again, just highlighting the importance of these long wavelengths. So now moving to the longer term kind of behavior as opposed to short term phenomena. So here I've divided it into galactic and extragalactic. Again, sorry about the buttons. So in the galaxy and the solar system, so starting at the bottom with the solar system, there can be, obviously there's the comets are active objects, asteroids, they're rotating and then moving around the sun, so studies of surface composition at long wavelengths would be important, time domain monitoring of those sources. Then there are various cases here involving young stars and protoplanetary disks, and I'll show an example of variability of protostars in a moment, but protostars also have outflows, so the similar explosive events. Some of these accretion events will also have impact on their disks and the chemistry in those disks, and so a couple of those these bullet points are about that aspect. But just to briefly explain this phenomenon, so this is an accretion outburst in a young star, and so this involves really just the inner few tenths of an AU or 1 AU, but the impact in the far infrared is more like a bolometer sort of effect, so that what I just illustrated in the last panel is going on right down in the center by the star. So there's an inner disk instability, but at the very youngest stages where we think these outbursts are more important and contribute to building up the central mass of the star, and they're more frequent, that outburst is embedded in the circumstellar material that is still infalling onto the disk. The disk is accreting onto the star. And we think that that process is important for building up the central stellar mass, as I said. And so it's really in the far infrared millimeter kind of range where you're seeing the impact of these outbursts, basically just propagating through all of this circumstellar dust. So you wouldn't see the optical, UV optical and near infrared inner disk behavior, but you would detect it at far infrared wavelengths. And this is an example from a program in which Doug Johnstone is involved of various protostars and their variability on timescales of days and years. And so the amplitudes here are factors of tens of percent to a few percent, and what's highlighted in the bottom panel here is monitoring at 2 different wavelengths. So the idea is that you would have a time delay between the light curve at one wavelength relative to the other, and that is a physical time delay. So as is illustrated here in a plot that I will not take the time to explain, but basically there's a time delay as the material propagates through that circumstellar envelope between the wavelengths. So this could be something that's studied. And then just saying briefly about moving to extragalactic science. So it's been demonstrated already here, some galaxies are very dusty. Obviously, you would not see variability of, from individual events in galaxies and the entire SED, but what one could measure with smaller beams would be the dust production in supernovae, AGN reverberation mapping, and black hole jet physics, which is very common to this wavelength range. Jets are variable, or jets can be studied at all wavelengths, obviously. And the last thing I wanted to point out is just AGN and reverberation mapping, where what one wants to study in this wavelength range is the synchrotron contribution to this and changes in where that turnover wavelength is telling you about the physics. And I'll just close with this slide, which differentiates between the longer term, persistent object monitoring and shorter term and target of opportunity responses, where what is common to the two is basically coverage of the sky and the ability to have this capability at multiple wavelengths. And so you can read the other technical constraints there. So the end.
Thank you, Lynn. So we have a monitoring. Is there anything online, Richard? No. Okay. So people online, please chirp up if you have a question. Do we have a question in the room? I think I frightened you all, and I'm sorry. Okay. All right.
Yeah, so maybe Lynn or somebody else in the room who has experience with it can say a few more words as to why is it so difficult to get it scheduled on the current facilities, because everybody is struggling with it, of course, between two sites. Yeah, well, with rapid response, but yeah, even on a single facility. I mean, of course, always the coordination between, say, X-rays and ground is difficult, but even on current telescopes, it seemed difficult to schedule.
I think we'd have to ask some of our directors in the room. I don't know if our radio directors are still here.
Are there any lessons that we can learn? Because I think it's an important question.
Yeah, I mean, right now it's more or less call your friends, in the optical near infrared, but at these wavelengths are differently scheduled, so I'd have to rely on others' expertise.
I hear silence from observatory directors, but this sounds like a topic maybe for the wider discussion. So let's move on. We have James now speaking on star formation. James Chibusi.
Okay, good evening, everyone. I will give a summary of what I think were the key issues that were discussed in the meeting. I don't know how long it would take for my slides to come up, but maybe as a disclaimer, I have to highlight that I attended the meeting from home, so it was middle of the night. If I've forgotten a few things, please do remind me.
Try to get to it first.
Yes. Yes. Okay, so there were 4 key things that I noted from the meeting that were key to this star formation community. And one of them is the fact that we need sensitivity to pick up a new cluster of newer objects that are forming newer star-forming regions to pick out a new class of young stellar objects. The second thing is that we need sensitivity on the spectral line to do more spectroscopy, to have higher sensitivity. The third thing was the need for follow-up to do time domain science to follow up on star formation. A bit of it has been mentioned. And the fourth is to do polarization. So these are the 4 key things that we consider as a requirement at the moment. But the key thing about star formation, of course, both at high redshift, is that we do want to look at high mass star formation We want to see how that affects the host galaxies. We also want to look at low mass star formation. The key questions involves what really regulates the star formation processes, and do we know if there are differences between the modes of star formation, both in terms of distributed versus the clustered star formation, and what are the determinant factors in the initial mass function, and how is the formation of a star connected to the formation of planets? I think that will be discussed by the next person. So these key questions are still pending. And of course, this is a borrowed slide from one of the presenters showing the spectrum of the dense molecular cloud. And the instruments you see here have finished their lifespan. Therefore, there needs to be replacements and new ones to take up the responsibility so that we can be able to reproduce focused attention on the areas of interest, especially in the molecules and also in the properties of the dust. Okay, so here is the first highlight, which is the new population of protostars that still highlights the disconnect between what we know currently and what we do not know. It is very easy for you to pick out class 2 YSOs, which are more evolved, and the class 1s to some extent, but the class 0 objects within these massive filaments that we see all around, which has been detected with Herschel, is still a huge missing link. There are very few of them. We don't have statistical information on their properties. We don't know if there are sub-properties within this population. And that is why we need additional sensitivity and probably higher resolution, which was not a strong factor in the discussion. The other key question is, why is star formation within the Milky Way inefficient? Why isn't it so efficient? Of course, this is one of the key discussions which was deliberated on. And if you look at this graph, you would see that if you take the AV values up to 5 magnitude, you will find 90% of the masses are below that value. So which shows the inefficiency of star formation within the Milky Way. And that's something we'd like to explore. If you also look at substructure scales, assuming you go higher resolutions and you peer deeper, at cloud scale, you might get star formation efficiencies between 3 to 6%. If you go down to dense core phase, you will find up to 50%. Of course, much of the mass reside within the dense cores, and you have more efficiency. So this would require additional sensitivity, if possible, better resolution to be explored. I'll go quickly to something that interests me, which has been mentioned a little bit, which is what we see in the time domain. Accretion bursts, which has been reported in low mass stars as FOs and XOs, have just in the last decade been discovered in massive stars. I'll skip how massive stars form. We can discuss this if you want, but we have that additional piece of the puzzle which we don't have now, which is that accretion burst being found in massive protostars. What does that mean? The simulation here done after the first accretion burst event was found in S255 massive star forming region, simply shows that the accretion rate is not constant. What you see is over time there is increase in accretion rate, and then it comes back after an accretion burst event, stays fairly stable, and then you have multiple accretion bursts, and this is the only way we can explain mass gain in massive protostars. However, we do not have many samples of this. At the moment, we have less than a dozen of these events, and I'll show you some of the examples. I would skip explaining the organization that is pushing to monitor masers in order to find flaring masers to search for accretion burst, because I have just 2 minutes. This is the first example, S255, where you could see the infrared flux change significantly during the quiescent phase and during the bursting phase. This was published by Garati, and we started looking for many more monitoring masers towards star-forming regions, and then we found the second one, which is this NGC 6334, which is my favorite object, measured distance to it while I was doing PhD, and that's what you find. In masers, it stays stable, and when you have this accretion burst event, the maser flares, and we were very fortunate to have, by chance, Crystal Brogan and Todd Hunter observing this source. They've done it in the past. You see also a flare in the dust continuum emission. How many of these happens within our Milky Way? What is the role of polarization in these accretion burst events? This is something we need to do in the time domain, and we will need lots of facilities playing in a synergy to be able to do this. Of course, this can lead to a lot more discovery and can affect the chemistry. This example is another accretion burst event, which was the most spectacular one. And in this case, we had a quick follow-up with ALMA, and we found a lot more new masers with ALMA, millimeter maser molecules. So that means the chemistry we know today is still incomplete until we look at these transient events and we're able to pick them up and study the details. Remember, this happens in some of them in few weeks, some of them last up to months. So if we miss any of the events, we miss a significant link in our understanding of high mass star formation. I'll just quickly page to the last part to show that we will need to get a huge amount of sample to be able to characterize and classify the samples or different kinds of accretion bursts, as has been done in the low mass star formation by the community. And also here we pointed out that there is need for spectroscopic and polarimetric observations to look at what is the role of magnetic field. We would like a quick response when there is an accretion burst, which is what everyone is asking of in the time domain. And hopefully we can narrow down our understanding of high mass star formation. Thank you.
Thank you, James. Question? Any questions online? No comments or questions online. Questions in the room? Okay, so now we move to the final scientific talk, which is Evine. Thank you, James. Talking about planet-forming disks.
All right, good. So these short talks were meant to give you a sort of a taste of the kind of science that was discussed and also some of the drivers for the recommendations that we make. Now I'm going to talk here about disks because I can't resist showing one slide about astrochemistry and telling you that that was of course also an integral part of the workshop, where you see both the gas phase molecules, simple, complex, also the solid state, ices, pHs, silicates, Forsterized that you see over there, and they all have their spectral diagnostics actually in the millimeter and the far infrared parts of the spectrum. Okay, good. So I'm actually going to talk about disks, and we had two wonderful talks actually at the workshop by young and mid-career scientists, Stefano Vaccini and Karen Neuberg. So I'm standing in for them, and unfortunately neither of them was able to come here. So we have studied disks with ALMA. We are studying disks at this very moment with JWST. But as we will see, we are missing actually quite a lot of the information. And both the far infrared, also NGVLA, and an upgraded ALMA are needed to address that. And in fact, the ELTs will also play an important role there by providing the highest spectral resolution from the ground. So we're really in a new era of science here. We're in a new era of observational planet formation with these wonderful images of structured disks that we have over here. Now remember, these are typically 40 milliarc second resolution data, so not yet at the ultimate of what ALMA can do, but that will take so much time and a higher frequency that those are still only a few that we can observe. So we're typically, even in the dust, still at sort of 6 AU resolution for the nearest system. But the big question is, of course, is this really evidence for forming planets? Are the planets there or not? And then also, you know, what is structure? Why are they at those distances? Why are the holes there where we see them? Maybe some of the holes may be much closer in, where we cannot see them yet because we don't have the spatial resolution. So there is clearly a need for zooming into the inner IAU, and there's a need for going to lower frequencies because in the inner part we actually get optically thick at millimeter wavelengths. So this just emphasizes that mismatch in the populations that we have at the moment, actually with ALMA. With ALMA, we are sort of here at, as I say, starting from about 10 AU. And the kind of structures that we've seen are usually interpreted with sort of sub-Jupiter planets that we have. Now, if you look actually at the exoplanet population, the observed mature exoplanet populations, these are of course the very youngest protoplanets, then you see that there's a mismatch. They are typically at between 1 and 10 AU. We are clearly not probing that part yet. So that is really the main driver here, that we want to go to that 1 to 10 AU region in order to see the young planet population. So here's one example of these very structured disks, how we're trying to infer actually whether there is a planet there. Well, we do that from the kinematics, and this is really absolutely gorgeous spectroscopy. We're just basically looking at the kinematics and the deviations from Kepler's laws. And you see here one example of red and blue shifted compared with the regular red-blue rotation motion. This is typically at the level of 1% of the total, but you see sort of these structures here of spirals and sometimes kinks that you see over here that could be indicative actually of forming planets there. So this is a clear case that drives the ALMA line sensitivity. We really need to go to the ALMA line sensitivity there in order to see that. Also, we need to get sensitivities down to Saturn mass. At the moment we are at Jupiter mass still. This is the case that, that Tony also showed for the NGVLA. This is for the inner part where the millimeter dust gets optically thick, and you still want to be able to probe there and see that same substructure and see maybe whether the terrestrial planets are forming there. Now this is a really hard case, and even NGVLA with a 10 times collecting area of ALMA is still going to need about 20 hours or more per source in order to do this. But the simulations show that yes, you can get down to about forming 10 Earth mass planets down at a few AU. So that is really one of the main drivers here for NGVLA. If you want to go to shorter distances, that is pushing up your observing times enormously. So this is really a major driving for the collecting area, the spatial resolution, and of course also the frequency range. Another way to look for forming planets is to look for their circumplanetary disks, and there's a big industry going on that. Not yet very successful. It's difficult to detect them, certainly difficult to detect with the current ALMA. From the ground, also with some of the optical infrared. This is certainly also an ELT METIS science case, but they turn out to be really hard to detect. So again, it's here both the frequency range and the sensitivity that is needed to improve on this. Then what I showed you so far was basically looking at carbon monoxide and looking at the sort of the deviations from capillary motion in the carbon monoxide. But if you want to know something about the material that forms planets, then you need to go to the other molecules. And as has been shown by ALMA, yes, you can do that, but it's hard. It's much harder than the continuum. Even now you need 20, 30 hours per one frequency setting in order to do this. So this is again a major driver for the increased individual line sensitivity that we need over here. So just to remind you that a lot of this chemistry and structure is set by the what happens also with the dust in the disk. So it's really this continuum sensitivity that we get with NGVLA at the longest wavelengths and in the millimeter range, together with the lines that tell us about how basically the planetesimals are growing and how that also affects the chemistry that we have in these disks. And again, ALMA, current ALMA is blind for that 1 to 10 AU region. that is really what we have to do. Okay, good. So turning to the far infrared, of course, will not spatially resolve it, but it will actually provide unique information on these disks. One of them is disk masses, a major question still at the moment. Uncertainties up to an order of magnitude from the traditional mass tracers. And one very good mass tracer is actually HD, because we know the D over H ratio quite well, at least in the solar neighborhood. And this is a very good, one of the main science drivers for the far infrared mission. The other science driver is the rest of the chemistry, especially water. What we are learning already from JWST is that there is a huge diversity actually in inner disk chemistry, much larger than we had expected. We're seeing not just water in the inner disks and evidence for things happening at the snow lines, but we're also having these very low mass stars that turn out to be water poor and very hydrocarbon rich. So this is clearly a case where the far infrared will play an important role in sort of understanding what the drivers are of this inner disk chemistry, from dust evolution and trapping to dust growth and settling and pile up at the snow line. At the moment, we have no clue yet exactly what is happening, but this is really where all of these facilities will interact together. Good, so this is sort of the final slide then on the far infrared part, where we have a number of these science cases, and of course also the solid states, the silicates, that come together and are unique really for the far infrared. Okay, so this was the slide with which Stefano actually ended, and the wish list basically summarizing how all of these facilities actually come together in addressing this very exciting new era of studying planet formation in action. Thank you very much.
Questions for Evine? Anybody online? Okay, so if there are no specific questions, I think this is the point where we can move to a general discussion. And so I'm actually going to hand the microphone, as it were, to Evine, who will lead the general discussion.
Right. Yes, so for the general discussion, actually, we still have about 15, 20 minutes. Yeah. I first asked some of the observatory directors to make some brief statements. I sent them the draft report beforehand, and so I would like to invite some of them to make some comments actually on what has been presented and what is in the report. Mark, you're on the front row.
Okay, so I certainly take the report under advisement. It's kind of difficult for me to make any comments one way or another right now because we're right in the middle of the selection process, and I really can't sort of comment on where we're going with the probes. But I will say, as a general sort of philosophy, I think the decadal survey did a really good job establishing this new probe line, and I certainly hope as we go to the next decade that's continued. Obviously, we can only pick one mission going forward, and right now we have both X-ray and far infrared missions in contention. So we'll have to see how this selection process plays out as we go forward. We will select 2 missions for the initial study, but that doesn't mean we're going to select one of each. We'll pick the top 2 based on the science and then technical feasibility. So I think that's about all I can really say right now.
Good, and if we stay with space for a second, then as you may have seen on one of the slides, the Japanese, who of course were very interested in Spica and far infrared for a long time, dating back decades to what was called H2L2 at some time. They actually have a small mid-infrared probe under discussion, under study at the moment, that's going to do more JWST wavelength range between 12 and 18 microns at very high spectral resolution. So they're going the direction, not so much of the far infrared, but very high spectral resolution, actually, to get the kinematics in the 12 to 18 micron range. From ESA, I see actually Michael is here. You want to say anything about what is going on in are you, would you be prepared to say one word about what is going on in Europe?
Well, I will say one word, or more than one word. I'm of course not speaking on behalf of ESA, but there's interest in the European community in the probes. So I think, whichever way that goes, there'll be European, interest in European participation there. And in terms of the ESA science program itself, there is of course a M-class mission call on the horizon. I think this was mentioned in the earlier session, and that might also be an opportunity. That would probably be the next. Oh, sorry. So of course ESA has a range of mission scales, much like NASA. There's the large-scale mission, the flagship missions, which at the moment are Lisa and Athena, and looking ahead to Voyage 2050, there'll be more. But there are also this medium-class size mission, which Spica, which was mentioned, was originally intended to be. So there will be another M-class mission call, and I think, depending, of course, on the timescale with the probe selection, that would be another opportunity potentially.
But one thing that came certainly up at the workshop was that thanks to the Spica development, there is a lot of expertise, also technical expertise, both in Europe and in Japan, and it would be really great to coordinate that and make use of each other's expertise, because there has been a huge technology development in the far infrared range to make that happen. Yeah. Okay, good. Well, turning to ground-based, Tony, you already in your last two slides said a little bit, but maybe you want to repeat some of that.
Sure. I mean, I think I appreciated the report. About 10 years ago, we did a fairly intensive process with the community to sort of look at what the future should be in centimeter and millimeter. And that process produced information and the decadal survey and where we are with our plans today. So I can kind of draw a smooth curve through all those things. And so I think in some sense we're kind of heading in the right direction. There is, of course, all of this surrounding environmental issue about the US process and that, but strategically and scientifically, I think we're kind of going in the right way. So I think I welcome the report, and I thought the conclusions are great. I do want to loop back to the thing that Lynn mentioned, this thing about transient science getting on things like ALMA. So I sent an email to my ALMA management colleagues about this, asking for ammunition, and they both came back and told me there is no problem. So there is at least a social problem, I would say. They pointed out that the transient science proposals are very well ranked on ALMA. They do actually about twice as well as the normal proposals. So just to refine the point, is the issue that the proposals are in and you ask to activate and they don't get activated, or they agree but it just doesn't get on the array? What is the detailed issue?
I'm certainly not no expert on this. I'm a little bit of an expert more on the high frequency part, which is another of the grumblings that we heard, both time domain and high frequency being difficult to schedule. Sometimes indeed you get time awarded, but then it's never executed, and so that is certainly an issue. I know that for the high frequency now, for the first cycle, first time, now improvements have been put in that many of us. We're noticing that we would get, low frequency band 3 data in absolutely perfect weather that would have been beautiful for sub-millimeter data. And so there was clearly something in the priority of the scheduling that was not doing the high frequency observations when the weather was right. But I think that has now improved for the last cycle. So we're really looking forward to getting more of the high frequency data. Okay, Brun, yeah? Okay.
Just because I happened to talk to him, that was actually saying that the response time was not quick enough to actually catch this variability in these stars. I mean, I'm not an expert on that. Oh, no, it's a matter of days. I mean, matter of less than a day, try to respond to the activation of the target of opportunity.
Okay, thanks. Bruno, you're representing ESO here.
Thank you. This is what you get when you're the only one traveling. There you go. That's right. So, well, thanks very much for the report. It's very interesting. It's actually quite timely. So Xavier announced at the European Astronomical Society meeting that ESO is starting to think about its next program. That's what we call it. So we're starting to think what is going to come after the ELT. And so we've discussed this with the ESO Council, and they agreed that we actually set up a way to come to a conclusion what it should be. And so I'm trying to read this so that I'm not making any mistakes. We're looking at what we would call the transformational facilities that would start operating in the 2040s. Okay, that's just the timescale that we have. It could be a new telescope facility on an existing or new observatory site. So we're trying to cast the net quite widely. It could be a significant upgrade of an existing facility that is co-owned by ESO. I heard something like this morning or this early afternoon already. But it could be other ideas as well. So we're looking for scientific topics that the community should come up to then decide where we're going to go. So we're setting up a process for the next 2 years, roughly, of community interactions, discussions with the community, scientific workshops to try to find out what's going to happen, what the scientific interests are 20 years from now. And it will be the science driver. That's the foremost thing. We will set up together with Council a senior committee fairly soon to evaluate proposals. And in about 2 to 3 years, we're going to call actually for letters of intent for specific facilities that ESO then would consider for the future. And so an ALMA upgrade is certainly possible, but there could be other things that people think are interesting. And so we'll just have to find out. So that's the process for the next 2 years. It's very interesting. We've never done this. ESO has never asked the community what it should be doing. It just said 100 meters is much better than anything else. And so we're now going to go to a process that will be quite interesting. So thank you.
Thank you very much, and good luck to ESO. Yeah, I understand we have comments online. Is it okay if we finish first with the observatory directors? Because we have 2 more. We had tried to get somebody from Japan here, but we haven't. So maybe we could get a NAOJ PDF file on. So the NAOJ actually sent basically a statement on behalf. Of course, Japan was very much represented at this particular workshop. So the first part talks a little bit about their process, and like in all the countries, it's a long process if you want to get something done, especially if you want to get something specifically done through roadmaps, through meetings, etc. But I think this is the important part where NEOJ recognizes the importance of thinking about ALMA in the 2040s. And that they will be looking into putting in on their time scale 2033 to 2042 something that they will call ALMA 3, basically is what they are starting to discuss now as a possibility for one of their next big investments. So you can read this here, but this gives you an impression that Japan, as of course one of the partners, East Asia as one of the partners in ALMA is also thinking about ALMA 2040 now. So that's very positive news. Okay, and then we haven't heard anything yet from China, but we have Louis Ho, who is actually also present at the meeting.
Should I stand up? I appreciate the opportunity to say a few words on behalf of the Chinese community. This is outside of my comfort zone. I would just preface by saying, relative to the US, Europe and Japan, the technical capabilities of China in this domain, I would say are relatively primitive. However, the appetite is large, the momentum is growing, and funding seems to be forthcoming. So in sort of order of priority, there are roughly 3 components to the roadmap. There's a space component, which will be a module, a spectrometer, a terahertz spectrometer that will be part of the Chinese space station telescope. That's a UV optical telescope, sort of the optical version of Raman, but it has enough reflectivity to direct some photons to a spectrometer. On a more serious side, China has been, Purple Mountain Observatory, been surveying for good sites in China. There's actually a fantastic site, a very, very large region in the Tibetan Plateau. It has many peaks in it. Several of them are as good as ALMA on paper in terms of PWV. And it's large enough for a possible array in the future. And then finally, China's had a long-term access and interest in Antarctica, Dome A, which is the best terahertz, even far infrared site on Earth. And they have ambitions to put an interferometer there in the long run. So if you can go to the next slide, just to show you. Oh, okay, right. This is just to say, so the Tibetan Plateau is huge and it has lots of good candidate sites. One of them has already been developed for a 15-meter telescope. That's called a XSMT. 15 meters happens to be the diameter, of course, of JCMT. So it's not impressive, but at a very good site and with a new generation of instruments, it can be scientifically still useful, just like JCMT is useful. In particular, it will be an important component of the next generation Event Horizon Telescope array. I think it's an interesting location as part of that node. The ambition is to add more elements to this 15 meters in the future, expand it into an array. And then there's the effort in domain that I mentioned. A lot of this technologically is driven by Purple Mountain Observatory. They've developed these niobium nitride SIS receivers that has a distinctive advantage in operate at 10K. That's extremely helpful for space. So on the Chinese Space Station Telescope, primarily it's a prototype to go for the carbon C1 line at 490 gigahertz. The 15-meter has a variety of instruments and receivers, basically from 100 to 460 gigahertz. I'm not going to go into the details. And then funding has been secured for the interferometer prototype in Dome. So these are the three sort of things that are happening in China.
Okay, thanks, Louis. That's very useful to hear because I think many of us are unaware as how much is happening also in China in this front. Good. We have just a couple of more minutes, but you say, Richard, there has been questions online. Yes. Yes, Claudia, go ahead and unmute your...
Hey. Can you hear me?
Go ahead, or otherwise write it in the chat, your question.
I wrote it in the chat.
Okay, can you show the chat? Can you read the chat? No, it's fine. It's perfectly fine if you read it in the chat. That's fine as well. I can read it. If we have... Okay, so let's see. Yes, jump to the latest, I would click on. Let's jump to the latest. Yeah. Oh. Yeah. Okay, 2 comments. We need to talk more about environmental sustainability. Yeah, that's an important point. I actually put it on one of my slides, that we should do this, the futures on a sustainable way. That's a very good point to put in the report. Maybe you can slide down a little bit more. Can we slide down? Can we slide down? Oh, okay, there. Well, okay. Okay, an update on the future 50-meter, 70-meter single dish. We were informed last month that our EU proposal to continue at last activities has been approved. A new project will start in 2025 and will bring the design to PDR level. The collaboration will expand to 20 partners, including EU Institute, University of Pretoria in South Africa, and 4 institutes of in Japan. The Atlassian LST. LST is the large submillimeter telescope in Japan, I think, or single dish telescope in Japan. Project will officially merge. Okay, good. Thank you very much, Claudia, for that update. That's very nice to hear that here. That's good. Also good that, because indeed we felt that there was still some more development and science needed to bring this to the PDR level, and it's very good to see that that is now happening. Yeah. Okay, good. Anybody else? Comments, questions? We still have a couple of minutes. Oh, sorry.
Evin, you mentioned that the goal of this meeting was not to prioritize the proposals. But then you said, but at a certain point, some prioritization will be needed. I mean, this prioritization happens within the US community with the decadal review, but many of these facilities are not US-based. So certainly, I don't know if this cannot be done right now, right? But somehow some coordination, some further coordination needs to be done with the European colleagues.
Yes, yes, and this is, of course, that kind of prioritization will be driven by the agencies, like ESO is going now start a process. That's basically the people who have the money, the funding. The IAU is not going to do that. As I said, we are just basically providing the ground for those discussions and those trade-offs. That is what we do over here. And hopefully by preparing the ground well, those discussions will be made easier than they would have been otherwise by preparing the ground for that. But yes, at some stage that will happen, and that will be either agency driven or in some other way driven. Yeah. Good. If not, then thanks everybody. We're, I think, right on time. Okay, thanks very much. And a big thanks again to Kafli for providing this. And I should also say that we're starting to think about the next one in probably 2 years. And if you have any suggestions for topics to discuss at that one focus, let us know as soon as possible.
Good. Wonderful.
Workshops.